Sir, I make you host, sir.
Is it visible now? Dr. Suresh, is
Yes,
it
sir.
visible?
Yes, sir.
Okay. So, good evening,
Sir, your
one and all.
okay. Sir, your screen is not visible, sir.
Okay, just one second. Let me check once. Please check again.
Yes, sir. It is visible, sir.
Good evening, one and all present over this online media. So, thanks to Vignan University for giving this opportunity to tell all about our research in the field of reconfigurable antennas to the participants or faculty members, those who are attending online of this institute, as well as from other universities or institutes. So this is a talk arranged like this. So we have whatever designed we have done in our group that we will discuss, as well as some designs from other universities I have taken, where I am collaborating. That also I'll tell. So basically, I used to conduct 2 short-term courses regularly. Few of faculty members, I think they might have attended this previously. So this course will be something different. Apart from that, we have added few recently published papers, and those designs will be definitely helpful to the young faculty members as well as students or research scholars, those who are attending. Coming to my topic, this is reconfigurable antennas, an overview. So no need to tell about me. Dr. Suresh has already elaborated. So coming to these fabricated antenna, we can see few antennas are planar antennas and few are DR, dielectric regenerator antennas. We can see the planar antennas, the radiating element or plane in the same plane with field line. This is all planar antennas, first, second, and fifth. Then second row, first, fourth, and fifth. All are planar antennas. And these 3 are dielectric regenerator antennas. Third one of the first row, second and third of second row. How this is different? Because dielectric regenerator antenna is made up of dielectric, which dielectric constants are more than 10. Normally in planar antenna or microstrip antenna, we use 2 to 10 permittivity or dielectric constant. So some books they write 2 to 10, or exactly we can say 1.2 or 1.5 onwards. As one, you can say that is not possible to make it dielectric. AR is not possible. So slighter more than that, foam onwards, we can consider the dielectric constant. Dielectric material for microstrip antenna, and similarly DRA will consider more than 10. Few examples, Teflon and other materials. Rogers 9.2 is also there. Many materials are there. So coming to need of reconfigurable antennas. Why we will go for reconfigurable antennas? While many antennas, planar antennas are available, DRS are available with excellent performances. So we need always multi-purpose applications which can provide intercompatibility for various platforms. That is the main purpose of going for reconfigurable antennas. And another one is agile electronics. It's adaptive signal processing, all those things where we can achieve compatible. Agile means compatibility, and we can adopt signal processing technique that will direct towards the reconfigurable antennas. Further, we can explain in this way. A reconfigurable antenna is one that has selectable or tunable fundamental characteristics. What are the fundamental characteristics? Operating frequency, impedance bandwidth, radiation pattern, polarization, all those are fundamental characteristics of an antenna. That can be variable in the form of variations. Typically, the goal is to change one or more of these characteristics independently of the others. This is very important. Reconfigurable antenna can provide substantial degrees of freedom and functionality to the end users. This is also another important point. So far, reconfigurable antenna is concerned. So coming to the applications, so various applications in communication, surveillance, navigation, and many wireless systems where multiple antennas that work at different frequency bands and polarizations. So this will replace multiple antennas. With one antenna, you can get many facilities or many benefits. We'll discuss step by step. The multiple antennas is strongly undesirable because it increases the size and cost. These are the demerits of multiple antennas. In addition, the electromagnetic interference between adjacent antennas may degrade the performance of the system. This is another demerit if you go for multiple antennas. An antenna that can be reconfigured to provide multiple functions, such as operating in different frequencies, producing different radiation patterns, or switching the polarization, will eliminate the need for multiple antennas and results in a reduction in the number of antennas. So, with these different radiation patterns, variation of frequency, and orientation of your pattern, and polarization, switching polarization means other linear polarization or circular polarization, again LSCP, left-handed circular polarization, again RSCP, right-handed circular polarization. In this direction, it will be very helpful. Next, reconfigurable antennas. So, few more points regarding reconfigurable antennas we'll discuss. These antennas taken birth many years ago and have received great attention. And this can be achieved by redistributing the currents on the antenna or electromagnetic fields in the antenna's aperture. This is the technique. So there are different mechanisms to achieve reconfigurability, such as switching and material tuning. So switching, as I told, we can go for different diodes, microwave diodes, maybe pin diode, maybe varactor diodes. So that can be used as switch, and different materials also can be used as substrates, which will help you to get reconfigurable or reconfigurability. Practically, the additional capabilities of the reconfigurable antenna should compensate the complexity and cost of the reconfiguration. Applications that drive the development of reconfigurable antennas include multifunctional wireless devices and ultra-wideband systems. So these are very good applications in the direction of multifunctional applications and bandwidth, you can say ultra-wideband system. So which is having a huge bandwidth, and the development of the reconfigurable antenna is highly dependent on the performance of the RF diodes and switches. Radio frequency diodes like pin diode, varactor diodes, and switches you can use MEMS and other switches also. Coming to reconfigure techniques, varieties of techniques are there. One is, as I told, RF MEMS, radio frequency, micro electromechanical systems that can be used as electrical switch, pin diode, varactor diode. That is the technique, electrical point of view. Optical point of view, optoconductive materials can be used. Physical structure point of view, structural alteration can be possible. One example I will tell to this slide. So with the extension of substrate also we can get frequency reconfigurability. So similarly, ferrites and liquid crystals materials will help to get reconfigurable systems. Types of reconfigurable antennas. So there are 4 types. First 3 are very normal, well-known: frequency reconfigurable antenna, polarization reconfigurable antenna, pattern reconfigurable antenna. So where we can vary frequency or get multiple bands, polarization, we can go for linear polarization, again circular polarization, LSCP, RSCP. Similarly, pattern reconfigurability, where we can get orientation radiation patterns with different angles, and hybrid is a new technique. Nowadays, we can get many papers on this hybrid reconfigurability in IEEE transactions and other journals. This is combination of frequency polarization together, or frequency polarization pattern altogether, or polarization pattern together. So like this, we can go for hybrid reconfigurable antennas also. Coming to frequency reconfigurable antenna, the frequency reconfiguration could be achieved by changing the operating frequency of the antenna while keeping the radiation properties unchanged. So one significant challenge that frequency reconfigurable antenna tried to meet by covering several frequency bands with a single efficient antenna. This is a very interesting technique. Such an antenna may not cover all bands simultaneously, but it could provide dynamically selectable narrow instantaneous bandwidth and would have better efficiency than a conventional multiband or wideband antenna. Furthermore, the narrow instantaneous frequency response decreases the need for filtering in the RF end, front end, due to the superior out-of-band suppression that provides over multiband and wideband antennas. Thus, the antenna provides greater versatility and flexibility to LS terminal to operate its several frequency bands. These are all the properties of reconfigurable antennas. So coming to different ways for achieving frequency reconfigurability. Switching between different external matching circuits. This is number 1. Number 2, using RF diodes, pin diodes, varactor diodes to alter the resonance length. Number 3, changing the properties of the substrate. As I mentioned, the permittivity or the height. And last is mechanical reconfiguration such as RF MEMS. So these 4 techniques we can use for frequency reconfigurability. Due to the rapid development of semiconductor and photoconductor technology, reconfigurable antennas can easily be manufactured using one of these switches. Switches, we can go, say, pin diode. Pin diode is most commonly used switching device. Why pin diodes are used? Normally, we put a question, while varactor diode is there, why pin diodes? So here are some advantages such as good reliability, low insertion loss, high switching speed, small size and low cost. This helps. These are the advantages over varactor diode. The operation of the pin diode requires a DC bias voltage to control it. So every time when we are using any diode, for DC biasing voltage is must. Coming to the equivalent circuit. So pin diode can be shown in terms of forward bias and reverse bias equivalent circuit. In the forward bias, you can see the inductance and resistance are in series, that is on condition. When reverse bias, some capacitance definitely will be developed across the resistors. So inductor series with R and C, they are in shunt, that will in off condition. So another point is mentioned over here. The quality factor of the pin diode decreases as the frequency increases. Therefore, the switch exhibits higher insertion loss at higher frequencies, which can negate the gain of the reconcilable antenna. So we have to take care of, so that we have to apply certain technique, the gain should be enhanced. Frequency reconfigurable antennas using birector diode. So here we have mentioned about the equivalent circuit of birector diode. So this is a capacitor, variable capacitor based diode. It has capacitance that varies with bias voltage, thus providing an electronically tunable reactive element. And birector diodes are usually made up of silicon or gallium arsenide semiconductor. The equivalent circuit for reverse bias we have shown here, a reverse bias case, it can be used in the circuit. So definitely one capacitor is there, Cj, Rj the resistor, and the series resistor is also there. So coming to frequency reconfigured by changing the properties of the substrate, how we can use substrate as the criteria for changing the for frequency reconfigurability. Nowadays, advances in several areas of material sciences have led to variety of new materials with strong potential applications to microwave and millimeter wave components. The high tunability and low dilatility losses are only desired properties of material which can be applied in the tunable microwave and millimeter wave devices. So if we consider one ferroelectric material, the driven energy required to change the property of material goes primarily to change the stored energy and is not dissipated in the ferroelectric material. So as a consequence, less power is required to control this property of material. Ferroelectric also allow the faster tuning compared to ferromagnetic materials. They have smaller and lighter structure and allow for high power capacity. So this way we can use varieties of materials, and we can go for composite materials also, if you consider the technique as substrate material. So coming to MEMS, so we can go for micro electromechanical systems, MEMS, or solid state switching device. RF MEMS are preferred due to monolithic integration capability with antenna segments along with their low loss and low power characteristics. Also, the potential of MEMS in avoiding nonlinearity and intermodulation effects is an important advantage over the solid state switching devices. So we can go for MEMS also. So next is polarization reconfigurable antenna. So I'll tell few lines about it. The polarization reconfigurable antennas are used to mitigate the fading caused by the multi-path propagation environment. That's why it will be this, in that direction it will be helpful to us. They have found applications in adaptive multiple input, multiple output, that is MIMO systems, which allow the dynamic change of the radiating properties of each antenna according to the fast changing channel condition. So these are the reasons why we will go for polarization reconfigurability. Design of frequency reconfigurable antenna. One example we'll take. So as I have told from the beginning, we'll go for two examples for each case. One is non-fractal, another will be fractal. All those fractal designs are recent designs, recently published in different journals from our group. And these non-fractals are little bit old designs. Those are also published in conferences and journals. Coming to this design of frequency reconfigurable antenna, one simple structure we have considered is a trapezoidal patch, or we can, from the shape, we can tell it hourglass shape patch. So concept starts from trapezoid. and low impedance open circuited transmission line we have considered here. And here you can see the field line is very microstrip field line, but it is considered here the quarter wave transformer for the matching purpose we have used, and different dimensions, say W, WC, WB, WA, L1, L2, all those things we have discussed in a table in the next slide, and how it will be helpful for reconfigurability using the substrate enhancement. That is a very interesting design. And this is a ground plane, full ground plane is considered here. And normally, sometimes we use partial ground planes also for benefit of bandwidth enhancement, impedance matching, all those things. So the antenna is designed using a FR4 low cost material and with a substrate thickness of 1.6 mm. This design is not very difficult. It's a simple design, but certain techniques are involved. So first of all, we should check when we will go for simulation, we should check whether S11 is achieved correctly or not within our operating band. That is very important. If you are achieving the S11 or reflection coefficient as per our requirement, then we proceed further. Otherwise, the design is having no meaning. So the reflection coefficient, you can see, always we consider the minus 10 dB line because it is related to return loss. The formula is known to everyone. So how minus 10 dB is achieved, everybody knows because all my faculty members are over here. So below minus 10 dB, we'll consider. In academic research, we are considered minus 10 dB. In industrial research, they normally consider minus 15 dB also. So you can see 2.38 gigahertz to 2.44 gigahertz within that range. We are getting the band, and the resonant frequency is at 2.41 gigahertz, and bandwidth is a little bit narrow, 2.48% bandwidth. Within this range, the bandwidth can be percentage bandwidth can be calculated this way: higher frequency minus lower frequency divided by the sector frequency into 100%. So this is very simple. Coming to the gain and radiation pattern. So from the 3D radiation pattern, we can get the gain also. So realized gain, we can get 2.544 dB here. And this rectangular plot from O-pole and cross-pole, we can see the below 3 dB line, we can consider the difference will give you the cross-polar level. So where we'll get 30 dB difference between co-pole and cross-pole. And if you consider from center to both the sides, you can see the beam width plus or minus 110 degrees. And here it is shown for different values of theta and phi. Legends are given. So next is up to that the simple design. But this comes your reconfigurability. How we make it reconfigurable? Using a vector diode. So here we have added one ground plane. GP1 is the original ground plane. GP2 with a certain parametric study as shown here in figure 10. And in between that, we have taken one diode. That is nothing but a vector diode. Details are given in further slides, next slides. But the data sheet from where we'll get the number, etc., and values. And this distance is W3 or width is W3. And W2 or GP2, here we have gone for parametric study. So with different values like 6 mm, 4.5 mm, 3 mm, 1 mm, 2.5 mm. So like this, plus minus within that, we have gone for parametric study, and accordingly, we have checked the reflection coefficient. Okay. So for this case, 2.5 is giving better reflection coefficient. So from this, we have considered a 2.5 millimeter value. So rest of the values also chosen using parameter studies. So coming to this vector diode, this is SMB2022. So from Skyworks solution incorporation. So it is placed between two ground plates. It is already I have discussed. And the important part is biased. So since it is a vector diode, so different values of capacitance are important with respect to capacitance. We have gone for parametric studies. So different values 7.41 picofarad, 0 volt, 4.414 picofarad, 2 volt with biasing voltage, different values, and corresponding reflection coefficient we have studied. M1 2.3, we got minus 29, M2 2.4350, minus 20.8435, like this, different values we got. So with respect to this, the capacitance, so we got 5 resonant frequencies: 2.395, 2.435, 2.445, 2.455, 2.47 gigahertz. So for the from the band 2.36 to 2.5, the complete band, within that band, all these 5 resonant frequencies we achieved. But that should be useful for your purpose. Application should be there. Otherwise, there is no meaning of designing all these things. Okay. So coming to this, next, radiation patterns and realized gain. So the capacitance value which is giving better result, that is 5.14 picofarad. So for that, the gain we are achieving 2.49 at frequency 2.47. We have considered one resonant frequency 2.47. Next one is 2.45, another resonant frequency. And for the same 2.54 picofarad for the capacitance value, and realized again we got 2.55 dB. So the performance table will give you the different values where for different values of capacitance, different resonant frequency and different bands, and what is the bandwidth and what are the realized gains. So from this, we can check 7.41, 5.14, 4.14, 3.49, 3.54. All these are different capacitance values, and accordingly, we are getting very nearer to 2.39 to 2.45 within that range resonant frequencies, and band is 2.36 to 2.43 band, or maximum band is 2.5. It is going. So, and bandwidth is again that is not very good bandwidth, but within 3 up 2 to 9, 2.9 or approximately within below 3% we are getting, and realized again also we are getting 2.48, 2.49 within that, or maximum is 2.55 we are getting. So the summary in this way, we can consider this way, that with a very low cost substrate at and design frequency 2.4 gigahertz, this has been designed. The peak realized gain at 2.55 dB to 2.48 dB, and the difference between co-pole and cross-pole is 30 dB, and beamwidth is plus minus 100 degree. And the different resonant frequency 2.36 gigahertz to 2.52 gigahertz, and we are getting omnidirectional radiation pattern and realized gain at 5 different frequencies. So based on these frequencies, which is required, so which gives the different applications. So at the end, it is there. So we can consider Wi-Fi application 2.412 to 2.483 gigahertz. This band will give you Wi-Fi applications. 2.402 gigahertz to 2.48 gigahertz will give you Bluetooth application, and 2.33 gigahertz to 2.4 gigahertz will give you WiMAX application. This way, this is very simple design, and one trial design for that PhD scholar. So he's Mr. Devakanto Behra. So he has not yet submitted his thesis, but with this and along with fabrication results, which is not shown here, he has published this work in IT map journal. So this comes next comes the recent design using fractal antenna. So before going for fractal antenna, I should tell a little bit about fractal geometry. You might be knowing. A fractal is a shape made up of parts similar to the whole geometry. The small part, same part is distributed throughout the geometry. That is nothing but a fractal. Fractal, we can go for an example like a structure of hill top, a tree leaf, a tree structure, a leaf of any tree. So like that, we can physically realize a fractal geometry. Repetition of similar geometry without altering the overall dimension of the structure. It has many properties such as self-similarity properties, self-affinity property, space-filling property, and statistical property. Many properties are there. Many theories also there. You can go through one book, very good book, that is written by Professor Raj Mitra, Frontiers of Electromagnetics. So you can go through that book. That total book is dedicated for fractal antennas. So why fractal antennas? Because it provides compactness, proper input impedance matching, provides narrowband, wideband, multiband. Many more applications are there. So coming to classification of fractal geometries, various types of fractal geometries are there. You can start from Sierpinski curve, then Sierpinski gasket, then Sierpinski carpet, Cantor dust, Cantor set, Koch snowflake, Koch curve, Pythagorean tree, Hilbert curve, Minkowski island. So all varieties are there. So we can consider a single variety or we have many varieties. When you will consider many structures, that will be a hybrid type. When you consider single, we can go for a single fractal geometry and make it use of an antenna also. So one example I have shown how to generate a Koch fractal. So certain geometry, certain theory is there behind the structure. Similarly, every structure is having certain theory and geometry. So formulas are available in that book and other journals, articles you can get it. So for a Koch fractal, very simple, one straight line is there, say, consider the length is L. And second, this is a zeroth iteration, no iteration or zeroth iteration. Then we'll go for first iteration. First iteration, we have divided into 3 parts. So each is L by 3 and center part is divided like this, L by 3 and L by 3. Each will be L by 3. So next iteration, so each segment will be again divided into L by 9. So again it will be divided into 3 parts. So it will be L by 9. So the center also will be divided into L by 9 or 3 parts. So it will be L by 9. So similarly, it will be a smaller portion. Then here also we can apply, further also we can apply, it can go for nth number, that will iteration will give you L by 32 by n. So, but feasibility should be there up to which iteration you will go and which will give you the better performance, plus it should be feasible for fabrication. That is very important. We can go to any iteration, but it should be easy to fabricate for the antenna purpose. So this is a small example. This is a small example. Coming to the design, this looks very good, but it is really not so simple. It is very complicated. So 2 types of fractals are used here. I'll go step by step. Evolution is there. So I'll explain thoroughly so that you can understand and you can work on it. So it is a Koch snowflake plus Sierpinski carpet. 2 types of fractals are used. These are the bigger ones are the Koch snowflake, and the inner walls star-shaped shorter ones are the smaller ones are the Sierpinski carpet. How it is designed, the total step-by-step design I will tell in further slide. This is a complete design, but diodes are there. This is one diode, this is another one, D1, D2, D3, D4. 4 diodes are used, and 1, 2, 3 biasing lines are there, where we can allow DC voltage, and along with DC voltage, inductors are ferrite in beads or inductors are there to help to pass the DC and block the AC components or antenna currents. So this is the front view, side view that here, second is the side view, third is the rear view. Rear view is the partial ground, we can slit here. The slit will help for bandwidth enhancement as well as proper mutual coupling and improvement gain also. So coming to more elaborately, it has been shown here. So this is D1, D2, segment 1, and segment 2 and segment 3 are connected here, and with biasing line 1 and 3. So again, another 2 diodes are there, D3 and D4. So segment 4 is again connected with biasing line 2. So pin diodes and ferrite bits are connected here. And here one equivalent circuit we have already discussed, but along with values it is there, and these values will be obtained from the data sheet. So here forward bias case, the L value is 0.6 nano Henry, and resistor is 2.5 ohm. Similarly, in reverse bias case, capacitance value is 0.15 picofarad, resistor value is 5 kilo ohm, and inductors value remains same. So the number is BAR50. So this is the number from you will get the pin diode from the data sheet. And coming to next slide, where we will get the specification. This is the basic specification for the antenna design, like substrate, dielectric material, substrate material, dielectric constant, and the loss tangent value, and operating frequency 1.4 GHz to 5 GHz. And all those length and width we have considered through parametric studies, different values are listed here. So coming to this step-by-step evaluation, which is very important, how to design it. So first of all, we have to go for the initial design. Then modification will be there in the second stage. First is zero iteration. This is coarse snowflake. So each side we have to apply this is a triangle. So then each side we have to apply the coarse snowflake. So here it is applied. Here L/3 value, like this it is applied. So this is iteration 1. Iteration 2, each smaller segment also will be applied coarse snowflake, so it will be more smaller triangles. So this is up to iteration 2 we have considered. Iteration 3 we have checked. We are not getting further modification or further performance is not so important for this kind of design, because we are not getting much variation. So up to iteration 2, and further another thing is complication will be more for fabrication point of view. So we have considered this iteration up to this. So based on this, we have got the reflection coefficient for iteration 0, iteration 1, iteration 2. So if you can see here, this blue line from minus 10 dB point of view, this gives a wider bandwidth. Okay, comparatively wider bandwidth. And coming to the next set, where co-Sierpinski is added here. So at the center, we have considered this Sierpinski factor, and this is the iteration 1, where iteration 2 each outer side or each segment we have given we have created with Koch-Sierpinski fractals. So this gives a hybrid type. Two types of fractals are used because it gives better performance in terms of frequency reconfigurability. So based on this, the second case, the iteration is 0, 1, 2, reflection coefficient. You can see. So this blue line from -10 to -10 dB line, you can see wider bandwidth is given. So this is all about the generation. Coming to next slide, we'll add diodes. So three cases we have considered: case 1, case 2, and case 3. So different frequencies we are getting based on the reflection coefficient. We are getting the different frequency bands. So case 1, all switches are off. This is the condition. So only feed line. This is off means this diode is not working. This is not working. This is not working. So only feed line will get the radiation. So it is radiating only feed line. So segment 1 is connected to feed line. Therefore, the current flows in this segment. In case 2, switch 1 and 2 are on. This is on. This is on. So this is the case 2. So this feed line along with this segment, this is radiating. So the current flows on segment 1, 2, and 3. So these three will be current will flow within these three segments. Finally, in case 3, since all pin diodes are switched on, the distribution on current is found at the whole fractal. You see, so whole this is on, this is on, this is on. This. So whole fractal is radiating. So this is the final one. So based on three cases, we will check what are the values or radiating frequency, resonant frequency, and what benefit we are getting. So coming to an equivalent circuit, only this design we have given the equivalent circuit. I'll explain little bit about this, and if required, you can go for Keysight ADS software, and you will go for design. And if you need more help, you can come to our lab. We can work on it. So first of all, this is the field line. So L and C will be there in series. And then for different values, I am telling from the very beginning. So I have not given any equation. You will get equation from this reference here, the below reference. It recently published AU LCBR journal. So you can check this article where all the equations are given. So first we will consider case 1 for case 1, because case 1 no all the diodes are off, so we will get a RLC circuit. So this dotted line, this block will come for case 1. This Z is for patch, and this is for case 1. So similarly, when we will go for case 2, D1, D2 will be on. So along with this and one block RLC, R2, L2, C2 block, and complete will give you the case 2. And when you go for case 3, again it will be added with D3 and D4, another block, and 3 more blocks we have considered for further bands or band enhancement we have considered. So as a whole, you can see case 3 is equivalent circuit for case 3. So complete equivalent circuit starting from input port to the 50 ohm matching line. This will give you the complete equivalent circuit. And you have to design using the Keysight ADS software, and tips are available, video lectures are available, and formula is available in this article, the cited article. And accordingly, we have to go for a reflection coefficient based on the HFSS software we have designed and compared with ADS. So you can see the reflection coefficient. Similarly, different values can be obtained from the formula of different formulas of RLC. So now coming to reflection coefficient with respect to switching condition, the case 1, case 2, case 3. The black is case 1. So the reflection coefficient, the below minus 10 dB is the operating is within 4 to 5 within that range, or end of the 3 gigahertz and just below 4. And this red one is case 2 and blue one is case 3. For different bands, we have to check the values and bandwidth. Similarly, this is the measured one. Measured one is case 1 for case 1, case 2, case 3 is shown. So in case 1, the reflection coefficient minus 10 dB line and bandwidth is giving 30% and 3.7 to 5 gigahertz, because this is only minus 10 dB line here is crossing here to here. So similarly in case 2 and case 3, so impedance bandwidth is 71% and 96% for case 3 with frequency band 1.7 to 3.55 gigahertz, 1.4 to 4.5 gigahertz respectively. And impedance bandwidth is 110% for overall, is observed for overall operation frequency band, that is 1.4 to 5 gigahertz if you consider the 4 complete band 1.4 to 5 gigahertz. So now consider the gain for 3 cases. So different values we are getting. Maximum cases all positive values, and here we have considered the peak realized gain 5.07 dBi at 1.8 gigahertz, that is the highest value. So for case 2, so since it is the highest value that we have noted, and other gain values are also can be observed from this plot. And this is the fabricated prototype and measurement setup in our anechoic chamber. So now radiation patterns, 2D radiation patterns, co-pole and cross-pole levels. This is the all measurement radiation patterns. So here legends are there, cross-polation YZ plane, co-polation YZ plane. The colors are defined here, black and red, then green, blue. So you can see the E plane and H plane patterns and the difference. So which will give you the XPD value, 31 dB for this case and 33 dB for second case, 3.8 gigahertz first plot, at 42.2 gigahertz second plot, and 2.7 gigahertz for third plot. Accordingly, cross polations are very good values, 31 dB, 33 dB, and 49 dB. So this is the performance table where overall summary you can get. The size is 70 cross 45 cross 1.6 millimeter cube. This is a frequency control type. The shape of the radiating element is star shape. Pin diodes, 4 pin diodes are used, and 2 types of fractal geometries are used. One is coarse snowflake, another is serpentine carpet. Number of iteration 2, and material 4.4, that is dielectric material substrate, and overall impedance bandwidth 110% within the band 3.7 to 5, 1.7, 3.55, 1.4 to 4, and peak realized gain. This is linear polarization, linearly polarized antenna, and application for wideband. Peak realized gain is 5.7 at 1.8 gigahertz. That is considered for highest value. So summary is like this. So this is one design of frequency recurve antenna, fractal based frequency recurve antenna. So then we'll go for a polarization recurve antenna. So here again 2 examples are there. One example is based on DRA, another example is based on fractal. So this is this design is of 2 PhD scholars worked on it. One is Dr. Runa Kumari. She is a faculty in BITS Pilani Hyderabad campus. Another student is Dr. Biswajit Dwivedi. He is a faculty in VIT Vellore. So initially it was started with Dr. Runa Kumari. So she did it this design at San Diego State University microwave lab with Professor Satish Sharma. So she had been to there for 2 months. She worked there. So the DRA array is excited by an aperture coupled feeding method to provide sufficient isolation between the dielectric resonator. So what is DRA or D? So dielectric resonator antenna is taking a dielectric material whose permittivity is more than 10. Okay, so or sometimes below 10 also we are considering, but this is not at all a metallic substrate, metallic patch over the substrate. So since we are not using any metallic patch, so losses are very minimum. No surface wave loss we will get. So losses is minimum, and bandwidth enhancement is more because height is there. So whereas copper plate, we are not considering the height of the or thickness of the copper plate. This is very, very minimum. But here, this is a 3D structure. So height, you will get the height of the DR also. So due to different aspects, we'll get more bandwidth. So the DRA array is excited by an aperture coupled feeding method here in this case to provide sufficient isolation between the dielectric resonator and the feed line or feed circuit. As the DRA are directly placed on the ground plane, so there is no source or surface wave which contributes to losses. All the DRs are excited in sequential rotation. This is called sequential feeding, 0, 90, 180, 270, again 0 or 360. So that gives circular polarization as well as linear polarization. This is very interesting design. So how to design? This is dominant mode is considered based on dominant mode. Direct formula is there available in textbook. So we can use this formula for resonant frequency, where two parameters R and H are important. R is the diameter of the cylindrical DR, and H is the height of the DR. So, and X1 double dash value can be obtained from the textbook 1.841, the Bessel's function, coefficient of Bessel's function, the first kind. So, coming to different value of RH, R by H ratio, different values of resonant frequency for the dominant mode can be obtained by. So, here we have considered two value 2 and DR value 20 mm. The operating frequency of from the design it is obtained 2.9 GHz. So, to enhance the bandwidth of the single element DRA, a hollow cylindrical portion is cut from the original segment. So, here we can consider small r is your value is there. So, all the specifications are available. Next few slides. So, coming to physical parameter, dielectric resonator specification is like this. Here we have considered 9.2. I told you below 10 also we are considering. Rogers 9.2 is considered. Radius capital R is 20 mm. Height of the DR 10 mm. And the radius of air gap is 4 mm. And height of the air gap is 5 mm. So ground plane dimension is like this, 160 cross 160. Dimension of the slot 14 cross 5. Microstrip feed line is like the dimension of feed line 48.25 millimeter cross 3.57. Length of the stop 3.5 mm. And the substrate is like this, Rogers attitude 3.55 and substrate dimension 160 cross 160 and the height is 1.6 mm. So here is the structure. This is the simulation structure. This is the fabricated one. So all this for enhancement of bandwidth, these slots are used, and this is sequential feed, and 4 feed lines are there. So 2 parts are there. So this without feed line simulation results are provided by Dr. Nakumari. Further, it is enhanced, but that results are not included here. So I'm using previous slides, which was used during my short-term course, and it is available. Dr. Biswajit's thesis, it is there. So, and this is fabricated again in San Diego State University. They are fabricated, and this is single element figure 29A is showing single element. B the complete rear view, and C the 4 element DRA, and D the fabricated elements. So this is based on the simulation results. So S11 value or S22, S33, S44. same curve with the minus 10 dB crossing around 2.67 to 4 within that range. So this is the hybrid mode, TE11 del dominant mode. So where cylindrical DRA provides different circular polarization LSCP and RSCP for different switching purpose. Here we have not used switching for different feeding conditions. So here is the performance table where we can see case 1, the port 1 provides magnitude and phase 10, port 2 00, port 3 180 and 00, it gives horizontal polarization. Similarly 00 190 00 1 270 vertical polarization. So these horizontal and vertical are from linear polarization, and case 3 gives 10 190 180 to 1270 RSCP, and when you will go for negative phase, so 10 1 minus 90 1 minus 181 270 LSCP. So with one structure or RS structure, we can get all varieties of polarization. So horizontal polarization, vertical polarization, RSCP, LSCP. So that gives you polarization recompatibility. So next part is the proposed by Dr. Biswajit. So this is just the basic part. Complete structures or complete circuit, it is present in his thesis, and I think that has been published or not, I have not remembered, but it is available in his thesis. So here, since we are having 4 feeding points, but source is 1, so how to design the feed line? This is very important part. So he proposed in this way. We will consider first input signal, input power is coming, then it will pass to the Wilkinson power divider. This is having output, it will give the equal amplitude and 0 phase difference. Then Shipman phase shifter is used, which gives equal amplitude and 180 degree phase difference. Then branch line coupler is used, which provides equal amplitude and 90 degree phase difference. So with this, he has designed, and 4 output powers can be obtained, and finally it will be fed to the array. So the output of the Wilkinson power divider is like this. It is fed again to Shipman phase, which gives 0 and 180 degree. Then it is fed to 1 branch line coupler. So 180 is fed to branch line coupler, one terminal. Another one is matched with a matched load, 50 ohm matched load, and similarly here 50 ohm matched load. So at the output of the branch line coupler, so one is 0, one is 90 degree, so which is 90 degree phase difference, equal amplitude. So we are getting terminal 2 and 3. So here it is 180 degrees fed at the input, and again 90 degree phase difference, 270 degree phase. We are getting here, and here 180 degree is already input at the input. So fifth terminal gives 180 degree phase. So accordingly 0 degree, 90 degree, 270 degree, 180 degree phase we can obtain. So this is the summary. So summary says different type of polarization, LSCP, RSCP, within the frequency range 2.7 to 4 gigahertz we can obtain. That will be helpful for radar band, LTE band, and other bands. So similarly, frequency agile antenna can be used in a wide operating range of 5 gigahertz covering full S band, C band. This antenna can be used for various wireless applications like WiMAX, Wi-Fi, WLAN, Bluetooth. So almost different bands of Wi-Fi, and C band downlink communication. And very important thing is that the size of antenna can be further miniaturized by using high dielectric constant ceramic materials. So it can be directly used for various handheld devices. So this is the non-fractal design. So coming to another fractal design. The polarization reconfiguration can be obtained using a very simple structure with one type of fractal here. This is not hybrid type fractal. We have used with only two diodes, the D1 and D2, and capacitance is used, C1, C2, two capacitors are used, and inductors are also used near to the bias lines. Three inductors are used. And this is again, post snowflake is used inner side of the hexagonal patch. Actually, the steps are in the next slide. And just a little bit I am telling you here. So first of all, one hexagonal patch is considered, and from center it has been edged out, and the inner side post fractal is applied. So after that, both the sides, when it is connected with a field line, so both the sides, two diodes are used, pin diodes are used, and field line also, and capacitor also used. So that it will allow the AC field to this connection, this segment, and here bias line is there. So with respect to two bias lines, voltage will be applied. So maybe with respect to 1, 2 or 2, 3, this is 1, 2 and 3. This is not 3, this is 1. So 1, 2, 3. So with respect to 1, 2 or 1, 3 or 2, 3, 2, 3 cannot be possible. So for one segment, so this and this and this and this. So when D1 will be on, this segment will work. This will give you LSCP. When D2 will be on, it will give you RSCP. So both will be on. This will complete design also will get. So that we'll consider. We'll see in next slide. And here another thing is that, so extensions are there. Two extensions are there. So that is helpful for achieving different polarization. Coming to specifications, this is a general specification of the patch, 32 cross 30 cross 1.6 millimeter substrate. So attitude substrate Rogers attitude we have considered 2.2 duality constant, loss tangent 0.0009, copper material 3 to 8 gigahertz, and different values of length and width are listed here. So coming to the iteration or evaluation. So here, this, as I told, so here originally one hexagonal structure is considered, and center, from the center it has been edged out, and both the sides diodes are connected, and field lines are there, or bias lines are there, one capacitor, two capacitors are there. So iteration 1, what happened? So inner side, the author is currently working under me as PhD scholar, Miss Khushbu Patel. So she did in this manner, applied the post snowflake inner side. This is the first iteration, and then second iteration, she applied again each small segment, again post snowflake, and as a result of which we have achieved this structure. So further we can proceed further iteration, but again, so performance is not much improved, and it will be more complicated also for fabrication. That is up to iteration 2 we have considered. So again, details I will tell in next few slides. So coming to this reflection coefficient for each iteration, iteration 0, iteration 1, and iteration 2. So iteration 2 is giving better bandwidth, and similarly axial ratio, also 3 dB axial ratio, we can see within 2 we are getting all the values, and gain value also for 0, 1, and 2 we are getting highest more than 5 dB we are also getting. So these all simulated results based on 3 iterations. So next is the ground plane. So first iteration or for antenna 1, this is one capacitor, one bias line, and this is a partial ground plane. Second case, this is a stop, the dotted line is a stop. So third case, one left side enhancement extension she has made, and fourth case, both the size extensions she has made. So to improve the impedance matching, a slit length of LF is etched in the ground plane and shown in the antenna 2. This is a slit. So and antenna 3 and 4, a triangular extension in the ground plane on the right and left added respectively. So this is published in Journal of Microwave and Wireless Technologies recently. So next is reflection coefficient, axial ratio, and gain. This is again based on switching condition. So antenna 1 shows the narrow frequency band, and after etching slit on the ground, impedance bandwidth is increased, displayed in antenna 2. So antenna 3 is a triangular extension, is ground plane widens. So axial ratio bandwidth enhances. So as a result, another dip is obtained at 5.5 GHz. So air bandwidth is increased substantially. Second triangular extension from left side gives the dip of air 5.5 to 4.4 GHz, creates another dip in 6.2 GHz. So air bandwidth of further extension gives 3.76 and 7.92 GHz. So it's performed by keeping D1 on and D2 off. For D1 on and D2 off for case 1, so all these values for antenna 1, 2, 3, reflection coefficient, axial ratio, and realized gain we have obtained. For different reasons, why she took all these, took the extensions, all those things. So it is mentioned over here. So coming to the CP, you can see the surface current distribution here. This is the condition for case 1 at 4.4 GHz and 6.2 GHz. Below case, the first case, the orientation you can see, bottom to top, then left to right, then bottom to top, then right to left. So this covers a LSCP. So similarly, this is again at 6.2 also. This gives LSCP. So both these cases, this gives left-handed circular polarization. So coming to case 2, same frequency 4.4 GHz and 6.2 GHz. There's a D1 off and D2 on. It will give you RSCP. You can see this way, the orientation this way, then this way, then this way, then this way. So similarly in 6.2 also, from right to left orientation, a counterclockwise. So it will give you RSCP. So coming to this reflection coefficient, this is for S1N plots. So for different lengths, we have checked variation of LE and LF. So we have considered the reflection coefficient. So that gives a better reflection coefficient for LE value 12 mm. So similarly, in here reflection coefficient simulated and measured cases for LSCP, RSCP is presented here. For LSCP mode, D1 on and D2 off, case 1, and simulated S11 with covers minus 10 dB covers 3 to 8 GHz. Similarly for RSCP, D1 off, D2 on, it covers 3 to 7.81, and the corresponding value LP mode, that is linear polarization mode, D1, D2 both on. So case 3, 3.6 to 6.5 GHz. So accordingly, it has been shown for different polarization conditions, and axial ratio also shown for circular polarization conditions. Okay, as shown here, the simulated axial ratio bandwidth is below 3 dB covers frequency for 3.6 to 6.9 GHz, 3.33 to 7.14 GHz for LSCP and RSCP modes. So realized gain for different LP, LSCP, RSCP for all polarization are plotted here. Peak realized gain case 1, case 2, case 3 are 4.75, 5.07, 3.8 dBi at 6.4, 6.7 and 6 GHz. And this is the fabricated prototype along with measurement setup in our anechoic chamber. So again, 2D radiation plot where we can check the cross polarization level for all the cases. D1 is off, D2 is on for RSCP, and for case 2 and case 1, D1 is on, D2 is off, LSCP, and for 4.2 GHz, 5.2 GHz, for the cross polarization levels are 21 dB. So that can be checked from the diagram easily, plot easily. So case 3 is the case of LP. So here cross polarization level for E and H for different frequency bands 4.4, 5.2, 5.8, 6 GHz. The cross polarization level is 38 dB. So this becomes a performance table where size is 32 cross 30 cross 1.6. This is frequency polarization, hexagonal shape, structural radiating element. Pin diodes are considered 2 numbers of pin diodes. Curve is considered as the fractal geometry. We have gone up to second iteration. Roser attitude is considered here as substrate material, and LSCP, RSCP, and LP polarizations are obtained with these are bands 3 to 7.91, 3 to 7.73, 3.54 to 6.7 GHz with impedance bandwidth 90%, 88.16% to 61.7%, and actual ratio bandwidth 62.86%, 7.78% for LSCP and RSCP. Peak realized gain 4.75, 5.07, 3.8 GHz for different frequencies like 6.2, 6.3, and 6 GHz. And basically, it is a wideband. So summary is like this, whatever I explained in the performance table. So coming to radiation pattern, recontrol antenna. Here again, non-fractal and fractal both are there. A very simple structure, Yagi-Uda antenna designed by Professor Satish Sharma and team. It is published in an international conference, IEEE international conference. Long back, since it is a very simple design, we have considered it, and one can go for this pattern recontrollability using this simple design also. So this is they have considered one directional end-fire radiation patterns for the Yagi-Uda antenna. So again, a structure they have considered, and they have considered only 2 elements. One is dipole, another is reflector and dipole. And directors are also there. They have considered only 2 elements. The elliptical length of the director and reflector elements are modified through the presence of pin diode. So reflector and one director. So they have used 4 diodes. Okay. So 4 pin diodes, of course. So switching diodes 1 and 2 on when we get. They have arranged such a manner. This is minus X direction, left side, and right side is plus X direction. And when diode 3 and 4 off. So accordingly, biasing arrangement will be there. They are not shown here. The beam directs towards the minus X direction. It is said to be side 1 is activated. So what happens? They are getting one radiation pattern due to diode 1 and 2 on one direction, and when diode 3 and 4 on in the opposite direction. So when diode 3 and 4 is on, instead diode 1 and 2 is in off condition, the beam is focused to plus X direction. That is, one will give you minus X direction, and another will give you plus X direction. So that is the flipping of radiation patterns. So these design dimensions antenna can be determined after extensive parametric study. So they have given here L0, L1, L2, L3, L4 and A, B, W values. So side 1 gives and side 2 taking the values or S1 values. So it is plotted at almost same we're getting, but S1 value is little bit different for 1 and 2 and frequency band is almost same or same. And resonant frequency is slightly different, 1.49, 1.5 and around very near to minus 15 dB or slightly less than minus 15 dB S1 they are getting. So this is the flipping. One is giving flipping to left side, another is flipping right side. They have considered 3 frequency bands. So one is 1.45 gigahertz, 1.5 gigahertz, 1.56 gigahertz. This flipped, one is flipped minus x direction, another flip is y direction, minus x plus x direction. So this side 1 is on state, side 2 is in on state. That means that D1 and D2 gives figure 49A and D3 and D4 on gives 49B. So here side 1 on, side 1 is the 3D radiation pattern. So flipping is like this. So beam peak direction are flipped when side 1 and side 2 excitation is switched, which confirms the pattern recoverability results. So here surface current distribution. So side 1 surface current distribution is shown here. For side 2 surface current distribution is shown in figure 52. So accordingly, radiation you will get or current flow you will get. So again, this is a simulated one. So when the summary is like this, so side 1 is on state, the antenna presents a matching bandwidth of 7.6% from 1.443 gigahertz to 1.558 gigahertz. And similarly, when side 2 is activated, the bandwidth achieved 8%, 1.44 to 1.56. When configuration of the antenna changes, the matching behavior remains almost same. The proposed radiation pattern recontrol antenna changes the direction of the pattern from plus xz to minus xz while maintaining the beam shape. Also, the front to back ratio of the first case side 1 is around 20 dB, 16 dB and 11 dB. For second case, these are 20 dB, 16 dB and 9 dB frequencies. At frequencies 1.45 gigahertz, 1.5 gigahertz. So this is very simple design for pattern recontrol condition. Next, again, one very complicated design, that is hybrid recontrol fractal antenna. So this gives multiple or pattern and polarization recontrollability. So here, just from the very beginning, I am telling you 4 diodes. The front view are used, and 4 pin diodes and inductors are also used. And so this is a side view, rear view. Another 2 diodes also are used. Okay, so details will go step by step from the design point of view, and important thing is very simple structure, but few extensions are added with Sierpinski gasket, Sierpinski carpet. So fractal structure. So then coming to this equivalent circuit of pin diode, we have already discussed. So this is on condition. This is right one is on condition, left one is off condition. So where in off condition we will get the capacitor across the resistor and with the series with one inductor, and on condition is L and R are series to each other. So values can be obtained from the data sheet. Here this is the equivalent circuit, and in this case 6 pin diodes are used. The model number is SMP1340040LF, are integrated to the patch to achieve the reconfigurability. A Ferrite bead 470 ohm impedance. Sorry, that is the 470 ohm, that is inductor. Inductor impedance is in series with pin diode for DC biasing and RF blocking choke is used. For DC bias line, very thin wires, 0.03 mm are used. This work is published in IEEE Asia Pacific Microwave Conference. My scholar, she attended this conference in Indonesia and presented there. So it will be published in IEEE Explore later on. So coming to next design, specification is 42 cross 31 cross 1.6 FR4 substrate, 4.4 dielectric constant, and loss tangent 0.02, and operating frequency 2 to 2.5, 3.4 to 4.1 gigahertz, 6.37 to 10.6 gigahertz. And accordingly, different parameters can be found out for length and width. So this started with a very simple structure, T-shaped structure. Okay, antenna 1 consists of a T-shaped radiating element. A microstrip field line is also connected and with a partial ground. Okay, so next is to achieve beam switching. Okay, or pattern. A rectangular stub is added in radiating patch, the second stage. So here rectangular stub is added. So third stage involves lowering the monopole's height. So top portion is edged out. So adding two triangular pieces of ground here. So ground extension is added here. So it is shown in the C55C, and this operates in X band 6 to 11 gigahertz, which is the design's upper band of the operation. The monopole split into two sections in the structure, the four stages. We can see four sections. So one structure is four stages. They are additionally connected with two pin diodes. So both the sides, and D3 and D4, and enable frequency recoverability of the design. So D3, D4 will be connected at the ground plane. Okay. So therefore antenna 4 can accomplish polarization pattern steering in both the lower and the higher bands. The final stage Sierpinski carpet fractal structure is applied. Here this is the Sierpinski here. So and here this is the separation where two diodes are added, D3 and D4. So reflection coefficient, axial ratio, and gain plots are there. So coming to different stages, antenna 1, 2, 3, 4, 5. So simulated reflection coefficient, axial ratio, realized gain are shown here. So it can be observed that after implementing various stages, its performance is enhanced in terms of S11, axial ratio, and realized gain. So next, coming to surface current distribution, where we can see when D1 on and D2 on. So this case will get the, so when D1 is on, we'll get the LSCP. So the 0, 90, 180, 270 will get LSCP. So this case, and when next figure, when D2 is on, we'll get the RSCP. So this way we'll get the RSCP. So, and this frequency band 3.9 gigahertz, it has been shown. So coming to next, D1 on, the case 3 and 4. So when D1 on LSCP and D2 on RSCP at frequency 9.8. So these are the surface current distribution for 0 degree, 90 degree, 180 and 270 degree. So this can be checked with the orientation of the vectorical orientation, the current distribution. So fabricated prototype measured setup are shown here. This is the prototype and this is the setup. So this figure shows the front and rear view of the prototype. And the biasing was used for supply DC power and RF switches and SMA connectors to antenna is positioned in aqueous chamber. So coming to reflection coefficient and axial ratio for simulated and measured results for 4 cases. The S1 results 6.3 to 10.7 gigahertz upper band, and that is 2.27 to 2.5 and 3.4 to 4.1 are the lower band. So results 7.4 and 10.2 gigahertz upper band, again 2.27, 2.5 and 3.45 to 4.2 is a lower band. So some overlappings are there in the band. So in RSCP and LSU state, there are two reconfigurable circular polarization operating states. Frequency regions of simulation values 3.8 and 4.1, 6, 9.7 and 9.9 gigahertz are there. So from these, for different cases, measured and simulated S1 value can be checked, and here axial ratio can be checked. So coming to realized gain for both the simulated 1, 2, 3 cases, here realized gain is shown, and 3D radiation patterns are shown here. So realized gain is around 9 dBi, and here 3D radiation pattern plots where two different cases are here, and you can check the 3D radiation pattern for the lower and upper band, which shows the pattern tilting of approximately plus 30 degree and minus 30 degree. So tilting is there, so that shows the pattern reconfigurability. So radiation pattern plots, this is a 2D plot where first case D1 is on and D2 is off, the LSCP, and second case D1 is off, D2 is on RSCP. The cross polar value is 20 dB. And this is simulation and measured for 0 degree, 90 degree LSCP, and RSCP have been shown. So this is the performance table where different states you can understand this way. The state 1 where D2 off and D1, D3, D4 on. This case gives LSCP. D1 off, D2, D3, D4 on gives RSCP. And D1 on, D2, D3, D4 off, LSCP. And D2 on others off, RSCP. So accordingly, we can get the impedance bandwidth 22% within this range, 18.6% within this range. So similarly, for different cases, it has been shown 50.2%, 49.8% for state 3 and 4. And axial ratio bandwidth 7.6% within the range 3.8 to 4.1. And state 2 also 3.8 to 4.1, 7.6%. And 9.7 to 9.9%. Sorry, this band is 9.7 to 9.99 gigahertz, 2.04%, and 9.7 to 9.9 gigahertz, 2.04%. So overlapping is this, and beam steering is plus 30 degree, minus 30 degree, plus 30 degree, minus 30 degree. And peak gain is 0.6 dBi, 1.1 to 9.6 dBi. So this is the summary. The proposed reconfigurable fractal monopole antenna is designed for a purpose substrate, and reflection coefficient 6.3 to 10.6 as upper band, and 2.27 to 2.5, 3.4 to 4.1 gigahertz lower band, and the air band axial ratio bandwidth is below 3 dB, covers frequency range from 3.8 to 4.1 and 9.6 to 9.9 gigahertz in the operational band. Peak release gain is 9 dBi, and gain can be increased by using different dielectric materials of substrate for the bands where we have achieved less gain. So this is the end, the final conclusion. The various types of reconfigurable antennas are discussed and design methodologies are described. DRA-based reconfigurable antennas are better than microstrip-based reconfigurable antenna due to minimum surface wave loss, as DR is non-metallic in nature. Reconfigurable antenna can be suitable for multifunction applications. And if you compare within the planar antennas, fractal reconfigurable antennas having better performance than non-fractal planar antennas. So these are the reference. So this reference, the contributors reference we have considered, and the First reference, it was published in a conference at IIT Bhubaneswar. Second one, IEEE AMC Bhubaneswar 2013. Third one, it was Professor Sharma and team. It was the proceeding of Anti-Propagation Society, and that was Florida in 2013. And the other references, Khushbu Patel et al. Reconfirmed fractal devices. This is a basic paper you can follow, which is published in IEEE Microwave magazine. And Khushbu Patel and others design and of band reconfigurable co-spectral antenna for wideband applications. So this is recently published in AEU Elsevier. Then next one is published in the International Journal of Microwave and Wireless Technologies. Next one is a conference, IEEE Asia Pacific Microwave Conference. So other two references from other authors. So thank you all. So if you have few queries, you can tell. So Dr. Suresh.
Sir, some of the participants have doubts. They have mentioned in the chat box, sir. I'm going to read it out one by one, sir. Madam Sridevi Kadiyam, she has one doubt regarding, sir, can you show where varactor diode and capacitance are used?
This is actually, if you go to the design, just 1 second, I'm showing the design. This is just what is the design where it is. This is the internal circuit. This here, this is the internal circuit, equivalent circuit. Okay, so when you will go for simulation, so different values will get there, and you have to vary accordingly. So that is a variable capacitor diode. Outside, you cannot find it is visible to the outside world. So this is inbuilt. So that is varicap or variable capacitor diode, the varactor diode. Okay. So simulation, you can do the things. During the simulation, you can get the different values. With respect to that, we have to get the different resonant frequencies, S1N values, all those things.
Sir, one more question, sir. Please tell the 110% bandwidth. It is by Sasista.
What is percentage bandwidth?
110% bandwidth. She is asking about 110% bandwidth.
100% bandwidth?
110% bandwidth, sir.
110%, sorry, 110%.
Yes, sir. Yes, sir.
Okay. Oh, 110% bandwidth. Okay, fine. So this is fractal, I think we have discussed. This is we discussed in fractal somewhere. Just 1 second. First fractal frequency control somewhere it is discussed. Just 1 second. This is 110%. So impedance bandwidth, you can calculate from here the reflection coefficient. So you can consider the measurement. If you consider the measurement, the lower frequency and higher frequency, the difference between higher frequency and lower frequency divided the resonant frequency. Here you can, if your peaks are more, so then average you can take. So from that you can calculate. Okay. So if it is a single frequency, center frequency, directly center frequency can be divided into 100%. Or if you are getting more dips or two dips, so you have to consider all the dips. Okay. So we take the average of that. Center frequency will be the average of the frequency, all the dips or resonant frequencies. That way we have to calculate the 110%.
Dear participants, you can ask any question regarding the session, whatever you have to this.
Sir, good evening. I have one question.
Okay.
When we design reconfigurable circuits, we need to ensure that proper biasing circuits are designed in order to
Yes.
apply DC voltage to varactor or pin diode. So, what considerations need to be made before we design the biasing circuit? What points we need to keep in mind when we design the biasing circuits, either for pin diodes or for varactor diodes?
Yes, yes. Biasing circuit is so you have to width and length, two things you have to check. So that we have to consider 0.03 mm, that we have to consider. So if you change that value, so there will be some variation in performance. So that will be there, and accordingly, the biasing line, proper inductor should be connected. That value you will get from data sheet. So all those things you have to check. So once simulation, if you get the proper performance, then you will go for fabrication.
Thank you, sir. Thank you for the information.
Okay.
Sir, good evening, sir.
Good evening.
Sir, author details for the fractal antenna mentioned. Can you please repeat?
How?
Author details. Book to refer the regarding
book.
fractal
That is Professor Raj Mitra. Raj Mitra and another author is there, I think. So that is Frontiers of Electromagnetics. Frontiers of Electromagnetics. Please check it with Google. So author is Raj Mitra and another author is there. Two authors are there, I think. So that I think that is out of print now. So e-copy you can check. Otherwise, that publisher, Tech House or some publisher, I don't know, remember perfectly. You can check with senior professors. They are having one copy, maybe.
Okay, sir. Sir, Raj Mitra and one more author, sir.
One more author is there. But Raj Mitra is a renowned professor that I remember his name. And foreign author.
Okay. Thank you, sir.
Yes.
ఇది అమ్మ నీతో చెప్పాలనుకుంటుంది ఇదిగో అమ్మతో మాట్లాడు రాక్షసి
So, further any queries, Dr. Suresh?
Any queries, participants? Okay, sir. No questions.
Okay.
Thank you for your valuable session by sharing your knowledge to our participants in the field of reconfigurable antennas and various patterns of antennas, and you have shown the various iterations of antennas. How can we design from step by step for different types of and different structured antennas? Thank you very much, sir. We have it is very pleasure for us to have such session with you, sir. Thank you very much, sir.
Thank you, Dr. Suresh, and thank you all for giving me an opportunity to present all related works from my group. Thank you all.
Thank you, sir. Thank you.
Thank you, sir.
Dear participants, now within the short duration of time, Dr. Vakula madam is going to join in our session for the next session. Okay, kindly be online. Thank you very much.
Thank you, sir.
Good evening, madam. I'm going to uh, brief about you for our participants.
Good evening.
Good evening, madam. Madam, let me share my screen
Okay.
for a few minutes in order to brief about you.
Okay.
Good evening, everyone. Now the next session is going to give by Dr. Vakula madam, who is professor and HOD for Department of ECE, NIT Warangal. It was a mistake written. And I'm going to give a small brief about her. Her area of interest is multiband antennas, fault diagnostics, neural networks, phase array antennas, ultra wideband antennas, metamaterials, substrate integrated waveguides, and she has done eight projects for various consultancy as well as for military of India, which are funded projects, and she got best paper award and best poster awards, and her publications includes in journals, conferences, book chapters, and patents. Especially the patent is F-shaped patch with reactive impedance surface and non-uniform superstrate for high gain and broadband circularly polarized antenna at 5 GHz and 6 GHz. Now she going to share her knowledge to our in the being a part of ATAL FTP. Thank you, madam. Thank you very much.
Thank you, sir, for the introduction.
Madam,
Now-
I'm going to share. I'm going to make you host.
Okay.
Now you can share your.
Okay.
Thank you.
Yeah. Share screen. Yes, share the screen. Yeah, is my screen visible?
Yes, sir. Yes, ma'am. Yes, ma'am.
Okay. Yeah. Is my voice audible?
Yes, ma'am.
Yes, madam.
Yeah, okay. Yeah, good evening, all the participants, and I thank the coordinators for giving me this session. My domain is in RF domain. So I want to give you a brief description of the design of metamaterials and antennas. And maybe here and there I can touch like where actually you can use the role of machine learning algorithms may come into picture while designing the metamaterials and antennas. So here there are two topics two words maybe in specific I want to say. One is the description of the metamaterials, and the other one is the antennas and the role of metamaterials in antennas. And maybe we can also analyze or enhance the use of different algorithms for optimization or getting a realistic characteristics of these two materials or two designs. One is, let us have a brief understanding or brief description of the metamaterials. After that, we'll go for the where this actually the metamaterial can be used for the antennas applications. And metamaterials, you know that metamaterial is not fixed to one domain. Like new networks, algorithms, machine learning algorithms, or any algorithms are not fixed to one domain. Similarly, metamaterials is also not fixed to one domain. You can have many applications of the metamaterials in different domains, and the application of metamaterials is also increasing vastly because of its inherent properties, where it has a wide number of applications. So first we'll see what is that material and a metamaterial. Basically, a material. Material is a composition of different atoms or molecules, and it has a periodic arrangement. Whatever the atom or the molecule you have, it is repeated periodically, and that arrangement is going to give a specific nature for that material. So each material has its different characteristics, different features. Like some can be solids, liquids, and gases. They have a different textures and different properties. But whatever the properties which are existing in nature are presented by the material. But now we are going to modify the properties of the material, by which you are going to call it as a metamaterial. So whatever the properties existing for that material, you are going to change the properties of the material in different ways, which cannot exist in nature. Those things you are going to modify by using a different sort of arrangement of the material. So that is a metamaterial. So this, as I mentioned, that this can be applied in different domains. But whatever the domain we are discussing, I am presenting here is for the electrical parameters is what we are going to discuss for the material. A material has different properties, the physical properties, but whatever the properties we are discussing in this domain or in this topic are the electrical properties of the metamaterial. So those properties we want to modify and develop a material called as a metamaterial. So the properties, electrical properties which are existing in nature can be modified by properly designing the metamaterial. So we can say that we know that the properties of the material are derived from its arrangement, periodic arrangement. We are going to develop a set of periodic arrangement by which we can control the electrical properties. So how to design these structures so that we can control the electrical properties? So because we are going to get a beyond properties, you are beyond. Meta is a Greek word and it is beyond the properties, which are not usually found in the nature, not observed in the constituent part materials. We are going to get those properties. That's why this meta word is used, which is a meta material. So this you can see, you have the arrangement of the material. You are going to modify that arrangement and derive additional properties. Now, if you want to design the additional properties, like how to design the additional properties, like which is not actually present. And one more word, what I said is like we are going to discuss only the electrical properties. So what are the electrical properties and how you can design a material so that it is going to get a different arrangement of properties. So for that purpose, we are going to take some unit cell, that means some basic structures we are going to design, and those basic structures we are going to arrange them in a periodic fashion on the material. So by which the electrical properties of the material are going to change. So what can be the basic structures by which you can get the material properties? One way of doing is like you have a dielectric material. The dielectric material will have certain electrical properties. If you want to change the electrical properties of the dielectric material, what is that you are going to make the material into a metamaterial by which the electrical properties of the dielectric is going to change, has to be changed. So this can be realized by designing a structures called as a unit cells. So these unit cells have some conducting properties. So these conducting properties of the unit cells are going to modify the electrical parameters of the dielectric. So for this requirement, what you are going to do is you are going to select different unit cell structures. And the basic requirement here is the unit cell structure. The size of the unit cell structure must be very much smaller than lambda. So what is the role of lambda here? You are going to take a dielectric material, and dielectric metal is going to have certain electrical properties. And these electrical properties are going to vary with the frequency at which you are going to use this particular material. So if you're going to select a particular frequency for to change the properties of the dielectric material, the size of the first requirement is the size of the unit cell, or the size of the structure what you are going to design must be very much less than lambda. This is the basic requirement. So the metametal is an artificial material in which the electromagnetic properties mu and epsilon can be controlled. As I mentioned, electrical properties. So what are the electrical properties of the material, a dielectric material? You have the two conditions. One is the which controls the electric field. One is which controls the magnetic field. So electrical field has the constant called as a epsilon. Magnetic field dependency has a constant called as mu. So these epsilon and mu are the two parameters what you want to control by designing this particular structure. Basically, a dielectric material has some value of mu and epsilon depending upon its behavior, depending upon its original arrangement of the molecules. But now what you are trying to do is you are going to change the value of mu and epsilon by designing additional unit cell conducting structures. So by these conducting structures, you are going to change mu and epsilon. That means you can change or you can control them. You can get different values. Usually mu and epsilon will be positive values. You can control them by the design of these unit cell structures. So this is the metamaterial. This is the first requirement. And this unit cell, you are also going to arrange them as a periodic arrays. So this periodic, not only the unit cell is the one parameter by which you are going to control the properties, the periodic arrangement of these cells will also have a effect on the value of mu and epsilon. So this periodic array of metallic resonant elements. So these are called as these unit cells are also called as a resonant element. What is meant by resonance? At a particular frequency, they are going to store. If they are storing means they are controlling the mu and epsilon. Previously, without these unit cells, you are going to have a particular behavior. With these unit cells,
Yes, sir, very correct.
with these unit cells, you are going to have a change. You are going to have a control on mu and epsilon. You are going to change the values. And it doesn't mean that you are going to place it any way, you will get the change of the mu and epsilon. But what is the basic requirement for mu and epsilon you want? And which values of mu and epsilon you want so that you can control those parameters? That's the next thing. And these small unit cells, they are also a resonant element and they must be very much smaller than lambda so that they can control the behavior. And because you are going to control the value of mu and epsilon, what is that you can say is you can manipulate the fields. You are going to change the fields and change its entire behavior. You are going to change the fields means mu and epsilon are changed. The behavior of the fields in the material is also going to change, by which you can extract many number of properties for the material, which becomes the application of the metamaterial. So what are the values of mu and epsilon you want in general? Which value of mu and epsilon are existing in nature and which value of mu and epsilon you want so that you can have the manipulation of the fields by which you can extract many properties which are not actually existing in the dielectric material. So what values of mu and epsilon you will have in general? Epsilon can be positive. Epsilon can be negative. Mu can be positive and mu can also be. Hello, sir. My screen sharing is disabled.
Madam, I'm going to mute the participants. Madam.
Okay.
Yes, madam. You can continue.
Yes. Yes. What are the different values of mu and epsilon you want? Like epsilon, the permittivity can be positive or the dielectric constant, and mu is positive. In general, for any dielectric material, the values of epsilon and mu are positive. So any dielectric material in general have epsilon greater than 0 and mu is greater than 0, by which you are also having the value of the refractive index of the material is a positive, and n is always greater than 0, refractive index. Velocity in free space by velocity in material by velocity in free space by velocity in the material, refractive index. So these are also called as the isotropic dielectrics, and these materials usually will have the right hand. They are called as the right hand materials, and they are also called as the forward wave propagation. That means wave is propagating in a particular direction. If you are having mu and epsilon in a dielectric material, wave can normally propagate electromagnetic wave. What I am speaking is an electromagnetic wave. Because of the placement of the conducting unit cells on the dielectric material, you will have the metamaterial. In general, these are the dielectric materials without the unit cells. So electromagnetic wave is going to propagate in the dielectric material. Now, if you take the epsilon negative value and mu is positive value, so this type of behavior is usually present for the metals. So metals at optical frequencies. So they have the metals have this type of values. Epsilon is negative, mu is positive for this metal, which are going to fall in the second quadrant. And refractive index is also positive. But what happens is in the metals, the wave is getting attenuated. You have the evanescent wave propagation only in the metals. So you will not have any electromagnetic wave propagation in the metals. You will have the electromagnetic wave propagation only in the dielectric, but you don't have the electromagnetic wave propagation in the metals. So the wave gets attenuated as it is traveling in the conductor. So those type of metals, they are also called as you also called as the plasma frequencies. They have the epsilon negative and mu greater than 0. This is one type of materials which are existing in nature only. The next one is you have the epsilon positive, mu is negative. If epsilon is positive and mu is negative, then also the refractive index is positive. What happens is for this also the electromagnetic wave is getting attenuated. It cannot travel longer distances. You have the wave propagation with attenuation. So wave cannot propagate in the material. So these type of materials which are actually existing in the nature are called as the ferrites or the ferrimagnetic materials. They have the evanescent wave. Wave cannot travel longer distances. So these three quadrants are existing in nature actually. And then what you are going to do is you are going to change the properties. You are going to have a control on the properties. You are going to have epsilon is also negative, mu is also negative, is usually not existing in nature, any material. You have the dielectrics, you have the metals, you have the ferrites. But this type of combination is not present. So what you are trying to do is you are going to take the dielectric and you are going to take the conducting unit cells and you are going to have both epsilon negative and mu negative. So if you can get a epsilon negative and mu negative, what is going to happen? These materials are called as the double negative materials. Double negative materials. So where both values mu and epsilon are less than 0, okay? And refractive index is also going to be negative. These are all called as a Vesselagos materials as by the scientist, and they are called as the left-hand materials, and they have the backward wave propagation. If the wave is, in general, it has to propagate in the dielectric in the forward direction. If these two values are becoming negative, wave starts propagating in the reverse direction. So this is a behavior of that particular combination of materials. So which is going to be of interest for many applications. You can have many applications by using this combination, epsilon negative and mu negative. So this is a region of interest for metamaterials. So what is happening here? Like you have the same thing. you have the conventional materials like the first quadrant. Wave is incident from air to the conventional dielectric material. You will have the transmission and you will have the reflection. So refraction and reflection is going to have, because partly it will get transmitted and partly it will get reflected. If you're going to, the wave is electromagnetic wave is incident on a plasma or metals, what happens? There will be complete reflection. There is no wave propagation. Even if it is traveling, it is getting attenuated. If the conductivity is infinite, we'll have total reflection. There will not be anything entering into the material. The same thing is going to happen for ferrites also. If incident, it will get reflected. There is no propagation. But what happens here, you see, if it is a double negative refractive index materials, if the wave is instant, it will get reflected partially and it will get transmission. But what is happening is the direction of transmission is changing. So this is the unique nature of this material, by which you are going to get the some other properties which are not possessed by this dielectric material. So that's why this this material which is having epsilon negative and mu negative is called as a metamaterial, and it is used for many applications, which we'll discuss later. So this is the first quadrant where we have the E and H is an electromagnetic wave. This is the direction of propagation, right hand, thumb, index finger and middle finger, leg. And this is the wave is traveling in this direction, energy is also traveling in this direction. This is called as the forward wave propagation, and where the phase and group velocities are in the same direction. Now, if you come to the second and third quadrant, anywhere there is no wave propagation. Next, second and fourth quadrant. Now you are going to come to the third quadrant. So in this, what is happening? This is E and this is H. The wave wave is traveling, energy is traveling in the forward direction. Wave will be traveling in the reverse direction. So previously, if this is E and this is H, wave is traveling in this direction. But if this is E, this is H, wave is going to travel in the backward direction. So that's why this is called as the left hand. This is satisfying the left hand rule, or it is also called as the backward wave. This is the forward wave. This is the backward wave. And here what you can say is backward wave means wave is traveling in this direction, but actually energy is still traveling in the forward direction only. So you will say that phase velocity is in the backward direction, whereas energy travel is in the forward direction. So this is the right hand forward wave. Left hand is the backward wave. That's why it is called as the backward wave propagation. Now, what is this phase velocity and group velocity? Phase velocity, we mentioned that this is the phase velocity, this is the group velocity. In this, phase and group velocities are the same. In this, phase velocity is in the backward direction, whereas the group velocity is in the forward direction. So what is the phase? Phase is, that means the phase of the wave is traveling in this direction, whereas the group, this is a group, both are traveling in the same direction. But here, if you say phase is changing in one direction and the group velocity is going in the other direction for the negative index materials. And one more thing is regarding the boundary conditions also. If this is the E and this is H, wave is traveling in this direction. So here what happens is, if this is E and this is H in the other direction, wave is going to travel in the reverse direction. So there is a change in the boundary conditions. Okay, here the boundary conditions are going to be different for the negative refractive index material compared with the other material. Due to the change in the boundary conditions, the direction of the wave is going in the backward direction. Now, how can you generate these type of negative mu and negative epsilon? How to design a material which has a negative mu and which has a negative epsilon is the point. So here you are going to call this as this is the how can we design a material which has a negative epsilon and negative mu. So let us first go for the design of this material which has a negative epsilon. So this is called as the Drude response. Let us take a material which has a we have a dielectric material. In this, we are going to place the conducting rods. So these rods are going to change the epsilon values, change the value of the epsilon. So this this is the instant electric field. By electric field is instant in this direction. If you're going to place the wires, this is called as the wire medium, or you can also have the rods. So what happens is the epsilon is changing as 1 minus omega p square by omega square. So when omega is greater than omega p, this value will be positive. When omega is less than omega p, this value becomes negative. So you are going to get a response of this fashion, where omega p is decided by the combination of these materials and the metallic configuration of these materials. So in a plasma, this is also called as the plasma frequency or the resonant frequency, plasma frequency. So for any material, for a in general, in a conductor, what happens is N is number of electrons, mass density, epsilon naught is the permittivity, and E is the charge of the electrons. For a conducting material, omega p is called as the plasma frequency, which is decided by the combinations of the metal. So for up to a particular frequency, epsilon is negative. Above a particular frequency, epsilon becomes positive. This omega p is called as the plasma frequency. So this is the region in which you are going to have the negative epsilon in general. So you want to realize this type of response by getting it or by using the wire medium or the rods. So these rods are called as the Drude-like response. This is a Drude response. We are going to simulate the Drude-like response by using this combination of wires. So at a particular frequency, which is less than omega p, plasma frequency, epsilon will be negative. For frequency omega greater than omega p, epsilon is going to be positive. So this omega p is decided by the arrangement and the dimensions of this wire medium. So where this is the 2 pi c square by epsilon naught ln of a by r, dimension and radius, spacing and radius. So this omega p is going to controlled by this arrangement, and you can have negative epsilon when frequency is less than omega p. You'll have positive epsilon when frequency is greater than omega p. So this way you can get a negative epsilon, generate a negative epsilon medium by using in the dielectric medium by using these conducting wires. So this was initially done by Brown, Rotman, and Pendry in these years. Next, you can also have the negative mu by using a split ring resonator. So let us see what is the split ring resonator, or what is a resonator in general. A resonator consists of an inductance and a combination of inductance and capacitance. So at the resonant frequency, what happens is current becomes infinity. So if current is varying, you can also, there will be a variation of the impedance. That means at resonance, this becomes omega, the reactance of inductance and capacitance will be opposite to each other. And omega naught is called as the resonant frequency. So this is the voltage present along the current loop, and this is the current. Now, what is that you can get by using this? How to develop this type of resonance structure? So here you are going to have a basic element where you can have, this is the inductance part, and this spacing is called as the current part. So this is called as the split ring, where you can get the electrical equivalent of the split ring is the inductance and capacitance. So the split is going to give the capacitance. This conductor is going to give the inductance effect. So inductance effect means you have the magnetic field surrounding this, you have the inductance effect. Capacitance effect means you have the electric field between these spaces, by which you have the capacitance effect. So this E, electric field present between these two spacings, is going to give the capacitance effect. The current flowing in this conductor will give the inductance, depends upon how much of magnetic field is enclosed by this conductor. So this type of combination, you are going to have a strong diamagnetic response over this region. That means above the resonant frequency over this region, you have a current, a strong diamagnetic response by which you can get the negative mu value. So this is developed by this is observed by the Pentry in 1999. So you want a strong diamagnetic response at these frequencies from omega naught to above omega naught. So where omega naught is the resonant frequency, above omega naught, you want to get a strong diamagnetic response, or you want a negative mu. So this can be realized where mu is equal to 1 minus f omega square by omega naught square by omega square by omega naught square. This type of result or response can be realized by using these structures, where here also you can control the omega naught, by which you can control at which frequency you want a negative mu. So this omega naught, if you control from omega naught to omega f, you will have a negative mu. So this f is a factor which is decided by the dimensions of the unit cell, and the direction of the magnetic field must be along this direction, so that current will be induced in the split rings. If current is induced in the split rings, that means you have the spacing here which have the capacitance, you have the conductor which have the inductance. So when at resonance, what happens? You have the maximum coupling of magnetic field by which you can generate the maximum current. So at these cases, you have the negative mu. So the value of omega naught is decided by these dimensions, which is given by these frequencies. You can actually calculate, where f is given by these dimensions. So between these two, from omega naught to omega f, you have the negative mu. So by which you can have a control on the value of mu for these materials. So omega naught and omega f depends on the geometry. That's why you are telling that you can control or you can decide at which frequencies you want a negative mu, at which frequencies you want a negative epsilon. So you are going to use the combination of these two structures. One is the rods and the split rings, by which rods control the epsilon and split rings control the mu. If you have a combination of these two, you are going to have negative mu and negative epsilon at the same frequency, by which you can get a double negative material, where you are going to have these different properties which are not actually present either in the dielectrics or in the metals or in the ferrites. So epsilon is less than 0. It is the silver Rotman rods or Penry rods, they are called as. Mu less than 0, you have the ferrite split rings. These are the mu less than 0. You are going to use the combination, which is given by Smith and Shelby et al. This is the first experiment. Combination of these two, it is going to give the negative materials. So these negative materials are also discussed in long back in 1904 by Lamb and Schuster and Veseligo. Mostly 1968. These are the all called as the Veseligos materials, both. When these two are 0, refractive index is also less than 0. That's the major thing. Now coming to the actual design of these metamaterials. So you can get them, actually first you must be able to design the metamaterial so that you can extract the properties. So maybe mostly in my slides, I'm not discussing what are the various properties you can realize by the metamaterials. Like you have the, due to this backward wave propagation, that part I'm not covering. Just right forward, I'm going for the design of the metamaterials and how you can apply them for the antennas for their performance enhancement. That much only I'm discussing here. I'm not going into more details of the additional properties, what you can realize by using the metamaterials. So next, let us straightforwardly go to the design of the unit cell. So here, this is called as a unit cell because the unit cell is the material which is going to change the values of mu and epsilon. So first you must be able to design a unit cell by which you can change the values of the epsilon and mu. So if you want to change the values, if you want to observe whether the values of mu and epsilon are changed or not, you must be able to realize its parameters. So which parameters you have to realize, or you have to simulate, or you have to observe to see the change in values of mu and epsilon becomes the next part. So here you have a metamaterial. So here in the metamaterial, this is a planar version of the metamaterial where you have the split rings. The ring is split. If there is no split, there is no capacitance effect, you will not have the resonance. Only with the split, you have the effect of the resonance. Here there are two split rings, one in this direction and one this direction. So the effect of these two split rings will cause a resonance where maximum coupling will be there. And you have a rod-like structure, planar structure. So where you are going to have this, where we are going to control the epsilon value. So this combination is simulated by using this simulation tool. And you must be able to realize its properties. Which properties you are going to, you have to define the ports, wave port, and then PEC, you have to define PEC and PMC. And then you have to first extract the properties. Which properties you are going to extract? You have to extract the reflection coefficient, transmission coefficient of those two, of that material by observing by making a electromagnetic wave incident. How much is getting reflected and how much is getting transmitted. So these parameters will give the behavior, like what is the reflection and what is the transmission variations are used to get actually the epsilon and mu values, because it's only the epsilon and mu values will decide the transmission and reflection. So you are going to do the other way. You are observing the transmission and reflection, and you are trying to extract the epsilon and mu value. So these two parameters must be plotted, transmission and reflection. When you are going to give the input at 1, how much is getting reflected. When you are going to give the input at port 1, how much is getting transmitted is S21. So these two are observed, both the magnitude and the angle. Two values you have to observe, because reflection, magnitude, and what phase it is getting reflected, transmission, magnitude, and what angle it is getting reflected. So these 4 parameters are measured or simulated. And then from this, you are going to extract the impedance, and then you are going to extract the N value and epsilon value and mu value. So using these expressions, you can get the real and imaginary parts of the permittivity and real and imaginary parts of the permeability. So here, if you see that this is the real value, this is the imaginary value. Over this range, the epsilon value is negative at this point. And at this point over this region, the mu value is negative. So mu value is negative. So observing from here to here, mu value is negative. So here, when there is a change, you will have the constant phase also. When it is negative, real value negative, phase is constant. You must have the constant phase. So over the values where which epsilon and mu are negative is the region. That means if they are occurring at the same frequencies, only that region you have to consider. If they are occurring at 2 different frequencies, then it is not a double negative material. So both the negative values must occur at the same frequency. Then that region becomes the double negative region. So initially you have to measure these values. You have to plot the value. You have to observe these values. The region over which both are negative is called as the double negative region, which can be application part. Anyway, I mentioned that we are not discussing where we can apply them, but we have to first see whether we can realize a double negative material. That's the first point. Design of the metamaterials. Next comes the, if you want to control the frequency, or you want to control, that means you want to get a predetermined range over which mu and epsilon are negative, then you have to change the dimensions of the unit cell. So for changing the dimensions of the unit cell is the place or is the location where you can apply using the different algorithms. So here optimization. So here comes the optimization. If you want to optimize, Like how you can optimize is you can optimize in different ways. You can use different number of optimization techniques available by which you can control the actually control the region over which you will get a double negative region. So here first you are going to give the unit cell, establish the relation between parameters, set a frequency for display, select the parameters for display. What is this optimization? How actually you have to get the optimization? Which parameter you want to observe, which parameter you want to control. So here, as I mentioned, that one thing is the dimensions. The dimensions of the unit cell is the input design values, and the parameters you are going to extract are the S parameters from which we have to get the values of the mu and epsilon. So here, these are the three things. The dimensions are related to the S11 from which you will get the mu and epsilon. These are the different levels. So here, if you want to optimize, you have to control the dimensions and you must be able to extract the mu and epsilon values by which you can get the desired or the selected range over which you can get the double negative. So here optimization plays a role here. Different algorithms, whatever are existing, can be used to actually do the optimization. Now here, there are other materials similar to the metamaterials which have the specific properties. Like we mentioned that the metamaterials, if you are saying a material is a metamaterial, means you have to prove that by showing the values of mu and epsilon. If they are negative, it becomes double negative. If they're positive, it's a forward medium. And like that, if you want to classify any material as a metamaterial, you can classify them by observing the values of mu and epsilon. Like these type of structures can also be used for realizing the different parameters. Like one such type of parameter is called as the high impedance surface. So here also you can use the unit cell, but the parameters you try to realize is not mu and epsilon. You are going to observe other properties of the material. One such type of property is called as the high impedance surfaces or artificial magnetic conductors. So what is a conductor? Generally, any material, a conducting material, you call it as a perfect electric conductor. This is regarding the conductors you are going to take. So you have a conductor is a perfect electric conductor if a wave is instant. Here, this is the electric field. What is that? Tangential electric field is continuous. Normal electric field is continuous for a perfect electric conductor. Tangential electric field is continuous and normal electric field is continuous for a perfect electric conductor. So you want to get a opposite of that. That is called as a magnetic conductor, in which you are going to get the reverse. Tangential magnetic field is continuous. Normal electric field is continuous. You are going to get the opposite properties. Then it becomes a artificial magnetic conductor. You are going to actually develop a such type of conductor. It is called as an artificial magnetic conductor. So here we want to realize, we want to actually modify the properties of the conductor also. We want to get the opposite properties. What is the advantages also? We can have a look at it. So this type of PMCs, where you are going to get the opposite boundary conditions for the opposite boundary conditions for the PMCs can be realized by using the arrangement of unit cells. So here also we are going to take the arrangement of the unit cells. This is the ground plane. This is a PMC. You have a dielectric. On the dielectric, you are again going to have these are called as the EBG structures or unit cell structures by which you have to realize the properties of a magnetic conductor. So what is the advantage here? So if you have an antenna, you are going to have the if a wave is instant, means it will get reflected with 180 degrees phase shift for the electric field. So if you're going to place, if you place a magnetic conductor, the reflection is without phase shift, without 180 degrees phase shift, with 0 degrees phase shift. So that is going to give additional benefits. So instead of PMC, if you have a AMC, you will have an additional benefit. Because if you want to place an antenna above a conducting plane, so because it is traveling here, it is getting 180 degrees reflected. So this distance must be, you have to maintain the distance such that these two waves are in phase here. So here, after from traveling here to here, 180 degrees, and by the time it travels here, two sides, it has to be again 180. So both of them will be in phase. So that in phase reflection has to be realized if you're going to place any antenna or any structure above a conducting sheet. So a specific distance must be maintained so that you have to get 180 degrees phase shift by the time it travels from here to here. So instead of that means some additional space, some spacing must be maintained if you want to place an antenna above the conductor. So instead of using a PEC, we are going to use a PMC because PMC is not going to introduce any phase shift. It's 0 degrees phase shift. So the spacing can be reduced. So this is the advantages of having an AMC instead of the PEC, perfect electric conductor. You have the PMC. PMC is the perfect magnetic conductor. Instead of a perfect magnetic conductor, you are calling it as an artificial magnetic conductor by which you can reduce the spacing between the antenna and the conducting plate. So this is what instant wave, and this has to be 180 degrees phase shift because there is 180 degrees. Both will be, you will have the constructive interference. So there must be a spacing of lambda by 4. But if you use a high impedance surface, instead of lambda by 4, because this is 0 degrees phase shift, you can make it very much smaller. Because it's 0 degrees phase shift, it can be placed very close to the conducting surface. This is called as a PEC. This is the PMC. And this PEC is having the 0 impedance. Impedance is 0. So where PMC is having the high impedance because we will have the inverse characteristics for them. So you are going to have the high impedance surface. So this is also called as the high impedance surface or PMC because artificial reason it is called as the AMC. And you are going to represent the characteristics of the artificial magnetic conductor. So what is the characteristic you want to say if you want to claim any material as a AMC? What is the parameter we have to show that it is an AMC? The parameter we have to show it's an AMC is the reflection. What is the angle of reflection? If the angle of reflection is 0 degrees, it says it is AMC. If the angle of reflection is 0 degrees, 180 degrees, it shows it is a PEC. So here, what the parameter, what you have to observe is the reflection, angle of angle of the reflected wave. So the angle of the reflected wave is 0. It's a PMC. Or if it varies over a particular range, this is a 0. Is a PMC. If it varies over a particular range, you are going to call it as an artificial magnetic conductor. If it is a minus 90 degrees, it is an inductance plane, plus 90 capacitance plane, or 180 degrees, it becomes a perfect inductor. So you can classify a material as a magnetic conductor by observing these characteristics. Again, this is realized by placing a conductor by a dielectric, and you are going to place some periodic structures. This is the other one. So these high impedance surfaces are usually realized by using these type of conductors, and there is a contact here. These are called as a mushroom-like structures. You have to observe the resonant frequency. You have to observe the angle of reflection. So angle of reflection is 0, it's PMC. It is 180, it is PEC. It in between, we are going to classify it as a AMC. So here, even these mushroom-like structures is going to have an capacitance effect and inductance. So this is the inductance and this is capacitance. So its behavior will be more visible at the resonant frequency. So this is, we can control again the frequencies over which you are going to have the 0 reflection. So these are the mushroom-like unit cell structures. So where the angle is going to vary, and you can control these mushroom-like structure. That means you have a conductor and you have contact from this conductor to the bottom conductor. So this angle you have to observe to prove that this is a AMC or PMC. Now, for both these structures, what are the applications where you can actually use them and how you can get a better properties? Both are the different ways, different versions or different perspectives of the similar structures. So here, whereas a metamaterial, you are going to place it on a dielectric, whereas a AMC, you are going to place a conductor, dielectric, and there you are going to have the unit cell structures, resonance structures. So applications, how many? There are many applications ranging from microwaves, terahertz to optical. So many applications, different frequencies ranges you can use. One is the shielding. Shielding means it will not allow going to the other domains. And low reflection materials like absorbers, everything will get absorbed. And novel substrates and superstates. By placing the superstates, you can have the focusing mechanism or divergence or convergence. These properties you can realize. And they can also be used as sensors. You can sense the different parameters, humidity. And you can also use them for antennas. Antenna is also one sort of the sensor which will sense electromagnetic wave. You can use them as a switch, electronic switch, and they are the perfect lenses. You can use them as a lens, proper lens, and resonators. These are some of the applications. We are not actually discussing the properties, but these are some of the domains in which you can use. And what is the domain and how you can use them for the antennas? Like these are the broad areas. The previous ones are the broad areas by which you can use the metamaterials. Now we are going to, as I mentioned, that it can be used in many domains, but we cannot. Each is a separate big domain. Now what I'm trying to do is only focus on the application in the antennas domain only. So how it can be used in the antennas domain? It can be used to make the antenna conformal and flexible. You can lower the antenna profile, conformability, and you can reduce the volume, weight, cost. By using this, you can actually reduce, because the one of the major drawback of the antenna is if you want to use it at a particular frequency, it must be lambda by 2 distance. So you can actually reduce its volume, weight, and cost by application of the metamaterials or the PMs, AMCs. In addition to the antenna, you can actually reduce its volume, weight, cost. And you can also improve the one restriction of the, or one limitation of the antenna is the bandwidth. You can also improve the bandwidth. Which bandwidth? Either the impedance bandwidth, phase bandwidth, or the gain bandwidth can be enhanced by using the access. Like you can use them, it is an accessory by which you can have a better performance in these domain, in these parameters, or in these variations. And enhance gain, suppressing mutual coupling. If there is a crosstalk between the antenna elements, you can suppress them. For any antennas, two antennas, there should not be communication between the two on the surface. Their signal will be either added in phase or out of phase, only in the free space. There should not be any communication between the two. So that mutual coupling has to be suppressed. If it is a mutual coupling, means that interference, the coupling is going to change the overall performance. And widening operating tuning range. You can increase the tuning range, and you can also control, like shaping, steering the beam. Like what are the potentials in antennas? Like we said that these are the different features. We said that whether we can use this or not. These are the metamaterials we have. What are the features of the metamaterials? They have the left-hand materials or negative index of refraction. The sizes must be much less than with backward propagation. Actually, they have a very narrow bandwidth. Metamaterials are having very narrow bandwidth. And their applications are, you can use them as lens, series fed array, shell of an antenna, and zeroth order resonant frequency with reduced size. And what about the application of the metamaterial, this one, AMCs, in the antennas? Electronic band gap structures, they have the pass and stop bands. They have the tunable impedance surfaces with the controllable reflection from 0 to 180 degrees, one or on order of 1/2 wavelength or more. But they are also having narrow and moderate operating bandwidth for applications purpose. They can be used for improving the directivity and efficiency. They can be used as a reflector, waveguide reflector horn. They can also be used as a frequency selective surfaces. Now, what are actually the challenges we mentioned in the antennas? One, we call it as a bandwidth gain, and the other one is a size and integration and the cost. These are the limitations by which we want to overcome these limitations by the application of either the metamaterials or the AMCs. Is it possible or not? So for antennas, bandwidth and gain, difficult but possible. Bandwidth gain is difficult. Size and volume promising, integration is promising, cost is possible, and overall you can use them, these AMCs and metamaterials for the antennas application. Okay. Now, where actually you can use them? Like you can use them where actually you want to use these materials. You can use them as a superstrate for covering lens and radome purpose. And they have, because they are the superstrate, they can control the reflection phase. And they can also be used as the AMCs. And you can also use them as a substrate in the ground plane. So in the substrate, we are using them the substrate and the ground plane, their directivity can be improved and low efficiency, and their low coupling can also be reduced. So there are two possibilities. I can use them as a substrate or ground plane, or you can actually use them on the patch also. Now, which quadrant you want to go? Whether this first quadrant, second quadrant, third quadrant, and fourth quadrant. As we mentioned that the second and fourth quadrant or there is no wave propagation. Only the promising one is the first and the third quadrant. In first, you have the epsilon positive and mu positive. In third, you have the epsilon negative and mu negative. These are entirely backward wave propagation or the negative refractive index regions. So if you're going for the first quadrant, what is that? Actually, epsilon is greater than 1 and mu is greater than 1. But there is a region where epsilon is near to 0. That means 0 to 1. Mu is near to 0. That means 0 to 1. So these regions are also of interest for many applications. So these are called as the near to 0 materials. Epsilon is near to 0 and mu is near to 0. So these regions are also of interest for the metamaterials applications. And this is totally a different domain where you have the epsilon and mu negative values. It has a negative refractive index. So these are the regions of interest. This is also epsilon negative, mu negative, or both negative, or not negative. Epsilon near to 0, mu near to 0, or both near to 0. This is the regions. These are also some of the promising regions of interest. Double positive, epsilon negative, mu negative, double negative. These region is called as the mu near to 0, epsilon near to 0. This is double, both are near to 0. These are the regions. Let us see some of the applications where you can use these materials, metamaterials or the AMCs. So there are some examples what I have shown here, like electrically large antennas and high gain antennas and low profile. So some of the things we'll see. So the first thing is, let us see one application where we have this is the unit cell designed. So the unit cell design must be in such a way that you have the splits and you have the conductors. So the split is going to give the capacitance effect and the conductor is going to give the inductance effect. The combination of each LNC will act like a resonator. So you are going to have the multiple resonances. If you have the multiple combinations, or the overall also it will resonate at a particular frequency. So this is a unit cell. And here, this is called as the effective medium ratio. This effective medium ratio is the ratio of wavelength by unit cell length. The effective medium ratio is an important factor in the metamaterial that governs the compactness of the metamaterial. So the more the compact, as well we said that the size must be very much smaller than wavelength. But here the more the smaller, the better the, smaller the sizes. So these smaller sizes are always preferable. So this must be the smaller size is possible. So the EMR must be as large as possible. Okay, this must be very small. So EMR must be as large. EMR value is more than 4, which is an ideal value. Then the negative permittivity is possible with the proposed design. The EMR of the proposed is 6.47. So usually whatever the unit cell you are designing, you have to see that the EMR is at least more than 4. So you can this is the unit cell, and you are going to further place the unit cell as a periodic array. So you have a vector network analyzer. You are going to place the metamaterial here in this waveguide. You are going to measure the connect it to the network analyzer. So this is the input and this is the output. So you are going to measure the reflection and you are going to measure the transmission, by which you can extract the parameters of the mu and epsilon. So this is the other parameter, the other unit cell, which is designed at the terahertz frequencies. So this this metamaterial is having pentaband. That means 5 resonances are present. Absorber. So here you are going to use this metamaterial as an absorber, where it absorbs 5 frequencies. Other frequencies it allows. So if a wave is instant on this, other frequencies will be reflected. If a wave is instant on this, it is going to give absorption at 5 frequencies at the terahertz domain. You can see that at each frequencies, each element is resonating, and you are having the absorption at 5 different frequencies, which is called as the pentaband. This is one more a mutual coupled concentric cross-line splittering resonator, which based on the epsilon negative material for a tri-band microwave applications. This is having a triple band absorption. So this is the unit cell, and this is the parameters what you can see. So here, if you want to develop a multiple resonances, so what you can go for is actually you are going to, the basic one is a splittering resonator. It will have a single. You can provide additional splits and additional rings, by which you will have the additional resonances, and the overlap of resonances is going to enhance the bandwidth, or these resonances are going to give the multi-band operation. So this is one such type of structure. And you can also see the equivalent, electrical equivalent of the unit cell, where you have this is the inductance. This is the inductance part. And you have the capacitance part, and you have the inductance part. You have one more capacitance here, and by which you can show the behavior of this unit cell. So you can see that the reflection coefficient is 0. Actually, if you want to show it as an absorption, if you want to show this as an absorption, you have to show that because on the back side of this, there will be a conductor. Everything will get reflected. So if you want to show it as an absorption, you have to plot the reflection coefficient. So at particular frequencies at which the reflection coefficient is 0 indicates that it's not reflecting, it is absorbing those particular resonant frequencies. You can see the fabricated model and the measurement using a VNA, where you are having 2 waveguides and metamaterial is placed in between. So it will as the basic bottom side, you have the metal, everything has to get reflected. You have placed that unit cell. So the reflection will not take place at this particular 3 frequencies, which indicates that there is an absorption. This is the measurement for the unit cell measurement is done by using the VNA. But if you are having a periodic structure, by using the waveguide structure. But if you are having a periodic array, you are going to do the measurement in an anechoic chamber, where you are going to use the 2 horn antennas. One is transmitting, and you can also measure the reflection. And other one is for measuring the S11 and S22. You are going to use the 2 horns, and you are going to measure the both frequencies. The other one is like how you can actually use it for the dipole antenna. Like if you want to use it as an AMC structure, what is the way you can use the AMC structure? That means to reduce the mutual coupling, or to use this as an AMC. You can see that you are having a dipole antenna here. This is the dipole. 2 fins CLL capacitive coupled loops. These are the capacitive coupled loops placed here. So these loops are the reflection parameter of the closed couple loops is observed, you can see that even for the reflection means you are going to do the similar measurement. You are going to instant an electromagnetic wave, you are going to observe this. So the reflected wave is having the zero phase shift at a particular range, where when the reflection phase angle is zero, you are going to call it as an AMC. This is called as a one-sided AMC. So backside, this is a one-sided AMC. And metamaterials, this will reduce. You are going to have the one-sided AMC means we can use this. This is the dipole. These are the AMCs, and these are the coppers. These are the AMCs. So you are going to use this dipole for radiation purpose. And the metamaterials as part of the antenna substrate. So if you are going to place the metamaterial as a part of, this is the antenna is present, you are going to place the metamaterials as a part of the antenna substrate, you can have a control on the resonant frequencies. That means you can see that it is resonating at the lower frequencies. So this is the electrical equivalent of the unit cell structure. So this is one more way of using the metamaterial for improving the gain. Like you are going to use the metamaterial as a superstate here. So here you have the conducting plane, you have the radiating patch. If you are going to place the metamaterials as a superstate, as we mentioned that you can use them either as a substrate and you can also use them as a superstate. If you are going to use them as a superstate, you can have the focusing effect. If it is more focused means you are going to send everything over a particular direction by which you are going to increase the gain. So metamaterial is used to improve the gain by using these structures as focusing lens. So you can have the superstate. These are the use of the metamaterial as a superstate. You are going to place it above the superstate here. So these will have the more focusing effect because you are placing as a superstate. You can improve the gain. This is one parameter what you can control. If you are going to use any metamaterial as a superstate, the parameter which you are controlling is the gain. If you are using them as a substrate, that means below the patch. If this is the patch, you are going to use, you can also use them as a substrate. Bottom, you have the ground plane. If you are going to use them as a substrate, you are actually controlling the impedance of the structure. So you have the control on the bandwidth, impedance bandwidth. That means resonance bandwidth, you can have a control if you are going to place this on the bottom of the substrate, on the patch. If you are going to place above the patch, you are going to control the gain. So both can be controlled if you are going to use both the superstate and substrate. Bottom substrate will control the bandwidth and superstate will control the gain. So you can use in both ways, substrate and superstate, both can be used. So this is a substrate. This is the superstate. In between you have the antenna. This is the antenna. Okay. In addition to using them as a substrate and superstate, you can also use it on the radiating patch. So using on the radiating patch, you are going to control the antenna size. You can reduce the size of the antenna if you're going to use this on the radiating patch. So two things, this is either you can use them as a superstate, substrate, and also the radiating patch. Superstate will affect the gain. Substrate will control the bandwidth. On the patch, it will control the dimensions. So you can have the control of different parameters by using them as superstate, substrate, and on the patches. So these are the different ways. And you can also have the multiple bands by using them on the same patch. The next one is you can have the, if you're going to use it, if you're using this, that means, let us see this case. Any loop, if it is lambda by lambda, this is of lambda length, you are going to have one full cycle variation. If it is 2 lambda length, you are going to have the 2 half cycle variations. If it is lambda by 2, you will have the 1 half cycle variation. If it is lambda by 10, you will have a constant current. So if you are going to have a constant current, then you are going to have a small loop. This is called as a small loop. That means over this loop, the phase shift is 0. Everything is constant. Everything is same. But here the phase is varying from 0 to maxima to 0. Here we are going to have 0 maxima, 0 maxima, two half cycles variations. So here you have the no phase variation. So you can realize a no phase variation also by using these metamaterial structures. So this has an advantage. This is called as a zero phase shift unit. There is no phase shift along the loop at a particular frequency. So you can also have a zero phase shift structure by using these small metamaterials placed here. So if you are having a zero phase shift, means constant current distribution will be there. So this type of realization can also be done by using these near field, can be used for the in RFID reader antennas, where you can have a constant phase shift. It will act like a small loop antenna. So this can be realized by placing a small metamaterial structures where the phase shift actually will become 0. If it is traveling from here to here, the phase shift is going to be 0. And along the total length, the phase is going to be same. And you can also use them for the generation of the two polarization. That's zero phase shift antenna can be used for when the antenna size is very electrically large. You can have the this type of zero phase shift antennas, and you can also have use this for the circularly polarization antennas, where you are going to have the two polarizations, two components, perpendicular components with 90 degrees phase shift. You can have the generation of the circular polarization. So other one is the use of the antennas, use of the metamaterials in the case of the Vivaldi antennas for focusing effect. So here, this is not actually the negative material. You are going to place these antennas and you are going to control the dielectric constant of the materials, by which you are going to have the better focusing of the Vivaldi antenna, by which you can improve the gain. So this is how you are going to have the enhanced gain enhanced antipodal tapered slot antenna. The other application of this metamaterial is you can actually mention that you can reduce the mutual coupling between the antennas. In the case of the MIMO antennas or even antenna arrays, you can you want to reduce, you don't want any mutual coupling between the antenna elements. But in antenna arrays, you are going to place them at a distance of λ/2, and we'll assume that there is no mutual coupling. But in the case of the MIMO antennas, there is no requirement that you don't have to place them at a distance of λ/2. You have to place them very close to each other. So when they are placed very close to each other, there is a mutual coupling between these two antennas. So this mutual coupling can actually be reduced if you're going to place some absorbers in between or insulators. So there is no contact between these two. This type of insulation can be realized by using the metamaterials. So you can place these materials here, PEC spacer, or you can use the AMC spacer, by which there is no contact between these two materials, by which you can reduce the AMC, reduce the mutual coupling. So this is the patch antennas. One more is with the high impedance surface, by which you can control the bandwidth of the resonant frequencies. This is with the substrate what we have discussed. These are the same antennas. So what is one more is you can place a dipole very close to the conductor or very close to the AMC. This is a reflector, so that the actual size of the antenna can be reduced. This is the dipole with AMC properties. These are the properties. Now, what is the limitations of the high impedance surface? Despite the unique properties of high impedance surfaces, they have limitations including angular dependence and limited bandwidth. Other limitations of passive high impedance surfaces are linear response and fixed working frequency, and usually hard to be addressed with only passive structures. However, it is possible to overcome these limitations by loading the surfaces with electronic devices, including pin diodes and varactor diodes and transistors. So the limitations can be overcome by using the switchable or tunable components. If you're going to use the tunable components, they are called as the active impedance surfaces, where the tuning will give a more broader range of working. So a non-linear self-tuning impedance surface created by attaching power sensing circuits beneath the surface and feeding back the corresponding controller voltages to the varactor diodes. You are going to have the high impedance surface. The impedance of the surface changes with the different levels of incident power, allowing for the properties such as self-focusing or surface or power of surface waves and power dependent absorption. So these are the high impedance surfaces where you can control the the properties over different frequency ranges. So you can actually control and you can also improve the bandwidth also by using this. So this is the placement of the surfaces beside the dipole, and this is the placement beside the between the MIMO antennas, and you can also place them in the waveguide structure, PEC structures. Okay, so these are called as the tunable metamaterials. Recently, some tunable metamaterials have been proposed by using various additional materials and structures such as liquid crystals, ferrites, varactors, capacitors, superconductors, MEMS, and tunable structures. Okay, so these are the most promising applications of the high impedance surfaces, tunable surfaces. So these are placed, you are placing the diodes between each structure. So by controlling this capacitance effect, you can control the frequencies also, frequency of operation. Okay. And you can also have the ferrites and wires can also achieve tunable properties, cladding wires dielectrics materials into the ferrites. The negative effect permeability was realized by using ferrites under the application of the magnet. You can also use the ferrites and control the bias, magnetic bias, by which you can control the properties. Okay. So these are the some of the metamaterials which are used for this what is that? This spiral antenna. So these are the different metamaterials used here by which you can have the control on these things. So these are the some of the active high impedance surfaces. So metamaterials have promising applications in antennas for improving parameters. A vast work is in progress among the research communities on metamaterials for many applications. Here I have focused only on the few applications, design and some of the applications for the basic applications of metamaterials for the antennas. And in the design, you can use different optimizations also, and you can have a control on various parameters of the antennas. And this is only a small topic what we have mentioned. Like you can use them for many other applications. Okay, thank you. Yeah, any questions? I think I'm concluding my presentation. Anything I can address or? Hello? Yeah, I finished my presentation.
Madam, I'm going to unmute the participants so that if they have any questions, they can
Yes,
ask.
okay, okay.
Dear participants, you can ask questions regarding the session, whatever Madam has presented today. I have unmuted your mics. Questions are welcome.
Good evening, madam.
Hello?
Good evening. I am Prashant Kulkarni from
Yeah.
NNRG.
Good evening.
I have a question, madam. While working on these metamaterials, if we can do simulation by using the available softwares, but what about the practical implementation? Whether the practical material is available for actual implementation in the market?
Yes, yes. Yeah, you are going to use the basic PCB material because whatever there are some existing PCB materials like you have the FR4, you have the RTG, right? Different variations of epsilon R and yes. different
So
variations.
those basic materials.
You can use the existing materials in the market.
Okay. But metamaterials are available actually.
That's what I mentioned in the beginning. Better materials, or you are going to realize them by using the dielectric materials.
Dielectric materials.
Dielectric
Okay.
materials with the unit cell structure becomes the metamaterial. You
Okay.
don't have anything like metamaterial. You can take
So
any
okay. So
dielectric
we have to
material.
realize.
You can realize them by using the existing dielectric materials. You are going to place a unit cell, it becomes a metamaterial.
Okay, madam. Okay. Thank you, madam.
Thank you.
Participants, if you have any queries, you can ask to madam.
Okay.
Namaste, madam.
Namaste.
Dear participants, madam, it is a very nice session for us. Being a initial days of this PhD days, recently I joined as a scholar in the JNT Anantapur. My area of interest is antennas only. By listening your session, I very much uh, I, increased my confidence so that I can do something. If I have any doubt here, if I have doubt in future stage, I can ask to madam so that she can clarify my doubts. By seeing your various presentations and by doing the antenna designing using metamaterials, by changing the variations of mu and epsilon values, we can how can we change the antenna electrical properties. It is very nice to hear your session, madam, and definitely it will be useful for session for us like us. Thank you very much, madam.
Thank you. Yeah, can I leave the session?
Okay. Dear participants, if you have any queries, you can ask to madam.
Yeah,
Okay,
thank
madam.
you for
Thank you,
giving
madam.
me this opportunity.
Thank
Yeah,
you, madam.
thank you
Thank
all.
you. Thank
Yeah.
you. Namaste, madam.
Thanks for your patience hearing. Thank you. I'm leaving.
Oh, thank you, madam. Thank you very much.